Bali, good morning.
Good morning, ma'am.
Attendees the joint event.
Yes, yeah. Also, I've started the streaming part.
I hope everything is done from our end to start the event now.
Yes, ma'am. Ma'am, we just need to know like who all are joining for the inaugural
That,
session.
okay. Just give me 2 minutes. Huh?
Yeah. Sure, ma'am. I guess Sanjeev Manha sir has joined. Good morning, sir.
Good morning, Manhas sir. Good morning, Peter sir. A very good morning, sir. Sir, your voice is not audible. We are not able to hear you, sir.
Okay. Is the audio any better now?
Sir,
Yes,
your
sir.
voice is okay. Yes, sir. We are able to hear you, sir.
Okay, very good. Yeah, I had was recording some stuff earlier, so good.
Yeah, sir. Good morning, sir. On behalf of all the academy, we welcome you all. So we are just waiting for the other academy as well as the dignitaries to join. Once joined, we will start the session, sir.
Yes,
In
yeah,
the
and I think
meantime, sir, can I request you, if possible, you can share your slides so that we can just check and we can start immediately with the event.
yes. Well, I sent my slide to Ganesan. I can also. I don't. Not sure. Let me see. I don't seem to have the.
Peter.
I think Sir Ganeshan sir has joined. Good morning, sir.
Yeah, good morning, Feroza. Yeah, I will. Peter, you sent the slide deck to me directly or uploaded in the Google folder?
I send it to you directly.
Oh, okay. I didn't see
Let,
that.
let me see. It just tells me that I need to change my system preferences to be able to present. So let me see if I can do that.
Feroza, all the PPTs we are uploading it in a Google folder. I will give you access to that right now. You can see
Okay,
it.
sure, sir. Sure, please.
Yeah, and you're welcome to put my slides in the Google folder.
Yeah, sure. Oh, I saw it right now. Oh, that's a 32 GB, 32.
Megabyte. Yeah. fairly big.
Okay, no, that's not big these days. Anyway, thanks, Peter.
Sure.
This is good.
Hello, Ganeshan sir.
Yes, Feroza?
Yes, so may we know the slides of Peter sir will be shared by at your end?
Yeah,
Yeah. Okay. Oh, then I'll share the presenter rights with you, sir.
yeah, sure.
Okay. Yeah, because I can do it, but it looks like I would have to quit and rejoin if I want to present.
Yeah. Okay.
Let me try that just in case. I'll be right back. I seem to be able to share now.
Sir, we have given you the sharing rights.
Yeah, and I have also changed the permissions on my end. See. Okay, can you see my presentation?
Yeah.
now?
Yeah.
Okay. I'm not currently in. Okay. So this looks okay, right?
Yep. Looks
All right.
good.
Okay, I'll stop for now. I think I'm only presenting at the top of the hour, right? There's the first.
Yeah. Yeah, you are the first presenter, Peter. Thank you
Yeah.
for that. I know it's too late for you, but sorry for that too.
Yeah, it's all right.
Good morning, all the respected dignitaries, all the representatives from different academy, our principal coordinator from different academies, and dear participant. We are waiting for our coordinators to join. Just give us 5 more minutes. In 5 minutes, we will be starting the event. Thank you for joining.
to all the respective dignitaries and the attendees. So we'll just wait for another 2 to 3 minutes. We'll be starting the inaugural session soon. Thank you for joining.
Hello, yeah, Ms. Pubali, can you please check NIT Patna coordinator Sangeeta Singh, ma'am? She joined, but I think so she is in the attendee list. From my end, I am not able to search. Can you please check?
Yeah, sure, ma'am, sure, ma'am.
Thank you.
Hello, Sangeeta, ma'am. So now you're in the panelist, I guess.
Yes, ma'am.
Yeah. Thank you, ma'am.
Yeah, Shubhari, if everybody joined, please start the session.
Yes, sir. Yes, sir.
A very good morning to all the respected dignitaries, principal coordinator of different academies, our coordinators from different academies for this program, our principal coordinator for this program, all the expert IBM representatives. A very good morning on behalf of Electronics and ICT Academy at IIT Guwahati, MNIT Jaipur, IIT Roorkee, NIT Patna, IIITDM Jabalpur. We are very happy to announce that for this 2-week faculty development program on open power ISA RISC architecture design enabled by the industry IBM, which is scheduled from 18th October, we are having a participation of around 441 participants across India. Where we are having participation from IIT Guwahati, NIT Patna, IIT Roorkee, MNIT Jaipur, and IIITDM Jabalpur. We are very happy to have such a large participation. On behalf of all the academies, I would request Dr. Gaurav Trivedi, sir, who is the principal coordinator for this particular event, to please say a few words, a few delighting words to the participant for this program. Gaurav, sir, please.
Thank you. Thank you, all the participants. Thank you, all my colleagues from different academic institutes of the country, and IBM. A very good morning to all of you. This particular course, which is precisely which we are organizing with the help of IBM and in association with IBM, is based on ISA RISC architecture. As you know that the computer architecture or the processor architecture is becoming very interesting, and day by day, I'm to say the RISC-V architecture or the RISC-V, which is the open source architecture, is taking the center stage. Similarly, there are many other famous architectures out there, and open power RISC architecture is one of them. So IBM precisely have come up with this architecture, and they have put this architecture in the public domain, which is much more efficient as compared to the RISC-V architecture and any other open source architecture available as of now. So this course, this particular course, which is actually introducing ISA RISC architecture, has become of paramount importance, because this is, as per my knowledge, this is the first pan-India course in India. So this is the first pan-India course on ISA RISC architecture. Mr. Ganeshan can correct me if I am wrong during his address to the audience. But this course precisely will give you chance to understand the nitty-gritties of the open power RISC architecture and enable you to design a processor by the end of this course. And I understand that this is very vital. Okay, because the hands-on sections and the other open source tools actually which we will be used for this will help you to drive this very much processor development at your end as well. So with this, I will not take much time, and I wish everybody a very good luck for this 2-week course. And if there is any issue regarding the course or if there is some issues coming up, you can always get back to me or Ms. Roja or Ms. Kubali, who are taking care of this course. We are always available to resolve the query, and so that your learning about this course and can become, you can say, interesting and seamless. So with this, once again, I wish everybody a very good luck. Thank you.
Thank you, sir. Thank you for your motivational words, sir. Now we are very happy to have with us Professor Sanjeev Manhas, sir, the Principal Coordinator from IIT Roorkee. Sir, may I request you to please say a few words, a few motivational words to the participant?
Yeah.
Thank you,
Good
sir.
morning. Thank you, Firoza, and thank you, Professor Gaurav, for taking sort of efforts to organize this program. And this is, as you mentioned, really a very unique. So this is really a sort of unique program and not done very often. We have conducted many other programs, but this is something like very unique, as well as offers the opportunity to the participants to learn something different and the latest in processor design. And the open architecture is becoming very popular. And in fact, there is a scope and a lot of work going on in designing solutions based on open architectures in emerging applications, particularly areas related to IoT and edge devices. So I feel that this is a very timely course to fulfill that gap for those participants and for those sort of candidates or those sort of interests where they want to work in utilizing this architecture in building specialized applications for IoT and enabling technologies. And as you can see from the curriculum, there is also very good sort of practice sessions or hands-on on implementing this particular architecture on FPGA. So I am sure that the participants will actually gain a very good confidence and sort of knowledge, as well as the practical hand-ons in design of RISC-based processors. And I'm also thankful and also very happy to see that, as IBM has come forward to be part of this course to, offer what is unique in the architecture and, let the participants learn from IBM itself also. So with this, I would like to again thank all of you and also welcome all the participants. We have some 80+ participants from IIT Roorkee, and I wish all the participants all the very best. If any issue you face for the participant at IIT Roorkee, please feel free to contact either our EICT team at Roorkee. So Mr. Sharad Sharma and Saurabh Jindal are the relevant person here. So you can also write to me. And thank you everybody for taking effort to organize this program. And thank you, Professor Gaurav also. Thank you very much and wish you all the best.
Sir, thank you, sir, for your information regarding this program, and thank you, sir, for the motivational word. So with this, we would like to invite Dr. Sangeeta Singh, ma'am, the joint coordinator for this particular program from NIT Patna, to please address to the participant. Sangeeta, ma'am, please.
It gives me great pleasure to welcome.
Ma'am, your voice is very low, ma'am.
It gives. Am I audible now?
Yes, ma'am. Now it is okay.
Thank you. Gives me a great pleasure to welcome you on the behalf of E&ICT Academy, NIT Patna, on the opening ceremony of this 2 weeks long online FDP on Open Power ISA and RISC Architecture Design, which is being jointly organized by IIT Guwahati, NIT Patna, MNIT Jaipur, IIT Roorkee, and IIIT Jaipur. I would like to welcome all the participants and I just wish them that they should have a 2 weeks long informative and fruitful time with us. And the workshop will include number of advanced topic regarding ISA RISC architectures and their assessments. So I would like to welcome all the experts also for sparing their valuable time for the learning of our participants. At the end, I would like to thank Dr. Gaurav Trivedi sir, Bharat sir, to take an initiative like this. And finally, I would like to thank my teammate, Dr. Pankaj Kumar, and E&ICT Guwahati E&ICT Guwahati team for organizing this event. Thank you, Firoza.
Thank you, ma'am. Thank you, ma'am. So, dear participant, this joint faculty development program will be from 18 to 29th of October, spending 40 hours of learning about the open power ISI, power innovation, processor development, associate design, fabrication, and programming in FPGA, gathering a cutting-edge insight about the industry expert and from academia. With this, we would like to invite our partner IBM for saying a few words about this program, as well as we would like to invite all the experts who are involved in this program. So may I request Ganeshan sir, sir, may I request you to please address to the participant and please give an insight about this program.
Thank you. Thank you,
Thank you,
Firoza,
sir.
for the wonderful program. Also, a lot of hard work, everyone from the curriculum side as well as from the organization side. It's a kind of a very big teamwork, like nearly 50 plus people. I'm really amazed, to see how integrated we are, to put together a program like this. The first time, the open power program in India, reaching out, several Indian students and faculties, and this is amazing. I'm very much happy about that. And I just want to give a brief intro about what is open power and where IBM is and all. The Open Power Foundation is a collaboration around Power ISA, instruction set architecture based products, initiated by IBM and several other partners, and announced as an Open Power Consortium on August 6, 2013. So it's actually 8 plus. It has been supporting and it has been innovating a lot of solutions on our platform. And IBM opened up the technologies surrounding the power architecture offerings, such as processor specification, firmware, and software with a liberal license, and will be using a collaborative development model with 300 plus partners. And that's where we are right now worldwide. Nearly 30 plus countries we have been working with, and working with the government, working with the universities and the industries. And the overall goal is to enable the systems vendor ecosystem to build their own customized server, networking, storage hardware for future data centers and cloud computing. These are all the main requirements, for driving us to create this, the Open Power Foundation, and many, partners around that too. So this program is like kind of there are like dozens of people put a lot of effort from India and from Europe and from US, and made it available for this venue, and that's a great one. I'd like to thank all the contributors to this. I really appreciate it. And this is a kind of really a good program with open source in mind, and that's where people like really contributed to this too. And I have a as part of this program, I have a distinguished research engineer from IBM. He has been with IBM for 30 years, 30 plus years. Dr. Peter Hofste, I don't need to say about him. He is well known to the processor architecture and accelerator community worldwide. He's sharing some of his the key experience, whatever he has been having with IBM, and also there are several other speakers going to be followed by him, and a lot of good lab, like I would say like nearly four to five labs, even with the server access as well as FPGA access kind of thing. Also, we set it up as part of the program, and completely like you're going to get a kind of a feast. It's a kind of a technology feast. For you to build create a concept and build a processor kind of idea. We are going to give it to you, and it's up to you like to really get onto it and get onto this ecosystem, and get connected with all these people who are going to be sharing their experiences and getting involved in this the 40 hours journey. And also we created a Slack channel. It is actually going to help you out a lot. It's not just for the 40 hours program who created it. There are like a 700 the developers as part of the Slack channel, Open Power Foundation Slack channel. Please do take a look and do join, and get involved, and you will get in our all kinds of the Power ISA staff, open course like a microwatt A2I and A2O course, and many more things. Certainly, it's a collaborative venue where the cutting edge insights of power innovation, process development, SoC design, fabrication, and programming in FPGA, everything you're going to learn in next 40 hours. With this, again, once again, I'd like to thank the organizer as well as contributors to this, the 40 hours curriculum, and also wish you all the best for the participants. Certainly, you'll have a wonderful, the journey for the next 40 hours. Thank you very much.
Thank you, sir. Thank you, sir, for giving insight about this program. Yeah, thanks a lot, sir. So we are also happy to inform you, all the participants, that we are having all the experts who are going to deliver this program has also joined for this inaugural session. In this journey of 2 weeks, we are having all the experts. We will be introducing all the experts. We will be discussing about their experiences, as well as they will discuss about the experiences they are having in the industry, and they will deliver their talk, as well as we will be having the lab session. So now I would request Dr. Gaurav Trivedi, sir, to please, please do the closing of the inaugural session, and we can invite our expert to start the session for day 1. So Gaurav, sir, please, sir.
Thank you, Ms. Roja. I really thank once again Mr. Ganeshan from IBM, Professor Sanjeev Manas from E&ICT Academy, IIT Roorkee, Dr. Sangeeta from from NIT Patna, and MNIT Jaipur, and IITDMJ for your contribution in this course, and all the participants who are registered for the greater learning. I'm very much hopeful, because I'm very much hopeful that all of you will really enjoy this course. And as Professor Manas has said, that this is the timely course where the processor architecture is playing a critical role right from the IoT devices to the high-end systems. And I do agree with that. And I know precisely this is this is going to be changed the world in near future, where the domain specific processors are also going to lead the way. So once again, I thank everybody who has you can say participate in the course, and I thank everybody who has tried their level best to make this course a successful one. When we will gather at the time of valedictory, I believe that all of you will be having a smiling face and a greater satisfaction with this course. So thank you, and wish you a very good luck. Thank you, Mr. Pooja.
Thank you, sir. So with this, we are coming to the end of the inaugural session. So from 10 a.m., we are having our expert talk by Dr. Peter, sir. So thank you all the dignitaries, the representative from all the academies, our principal coordinators from all the academies, and our respective expert for joining us for this inaugural session. Now there is an important announcement for all the participants. We would request you all to please note that the Q&A section has been enabled for all the participants. So to put the queries in the Q&A section, your queries will be addressed towards the end of the session. So I request all the participants to put the query in the Q&A section. There is another important announcement for all of you that you all have to maintain an attendance of 75% and has to appear in all the quizzes that will be conducted throughout the session. After getting satisfactory result in the quiz, as well as after having sufficient attendance for the session, you will be awarded the certificate. So this is a humble request to all the participants to please be attentive in the class and please attend both the quizzes. The quizzes timing will be announced in due time and during the session. The YouTube channel is also live. In case if you miss any part of the session, you can visit our YouTube channel. The sessions will be recorded in the YouTube channel, and anytime you can use that YouTube channel as a reference. The slides for the slides of the expert will be shared to all of you through the Google Drive link. You can access the Drive link and can download the slides. And also, there is an another important announcement regarding this WebEx. You all are requested to please join the WebEx by using your registered email ID, because we will be monitoring the attendance against the registered email ID. So all of you are requested to please join by using your registered email ID. So thank you. In coming 2 minutes, we will be starting the session. So I request you all to please rejoin if you have not joined from your registered email ID. The session will start in 2 minutes. Thank you. So good morning all again. So we are starting with the day 1 first session. I may request Dr. Gaurav Trivedi sir to please introduce our expert for the first session, sir. Over to you, Gaurav sir.
Thank you, Ms. Furoja. It's my pleasure to introduce Dr. Peter. Dr. Peter is the best known for his contribution to heterogeneous computing as a chief architect of the synergetic processor elements in the cell broadband engine processor used in Sony PlayStation and the first supercomputer to reach sustained petaflop operation. After returning to IBM research in 2011, he has focused on optimizing. The system roadmap for big data, analytics, and cloud, including the use of accelerated compute. His early research work on coherently attached reconfigurable acceleration on Power 7 paved the way for the new coherent attached processor interface on Power 8. Dr. Peter is an IBM master inventor with more than 100 issued patents. So, with such a you can say well-renowned and an intensely renowned person, we are going to start our first session. And a very good morning to you, Professor Peter. And I hand over the session to you. Thank you for your presence, and thank you attending this session for enlightening everybody with your knowledge. Thank you.
Thank you, Dr. Trivedi. So it's my pleasure to do the inaugural session for this course. So what I will do is I will talk a bit about the power instruction set architecture and open power, and then I will cover some of the cores that are available in open source. And then finally, I'll talk a bit about OpenCAPI. There is another course that I'm involved in where we are looking at the development of accelerators rather than processor cores. And I imagine that some of you may be interested in that. So I'll say a few words about it. First off, as you've already probably heard, you know, the open power is a community, and if you are interested in participating in that community, I would urge you to go to the openpowerfoundation.org and join. And membership is free for associate and academic members. So as I mentioned, in this talk, I'll try to cover the open power instruction set architecture, and I'll talk about some of the cores, and then I'll mention OpenCAPI. So this talk that I'm doing here is borrowing heavily from 3 other talks, the first of which is a talk by Brian Tomto at the Open Power, at the International Conference on Supercomputing in 2020 about the Open Power ISA. And also here you can see where you can download the formal version of the ISA, as well as a link on Wikipedia. So I will only be able to cover a summary of that talk, but so I'll be going over a number of the slides. So the RISC architecture goes back to actually earlier than the 1985, where on the right-hand side this slide starts. In 1974, IBM was attempting to develop a telephone switch that was supposed to be able to handle something like 300 calls a second. And in order to control that switch, IBM needed a faster microprocessor than was available. So that work in 1974 led to the first generation RISC processor. And even though that telephone switch ended up not being commercialized, the microprocessor project lived on. It then turned into the 801 project, named after one of the buildings in Fishkill, New York, with IBM Research. And then from that, it eventually turned into the RS6000 and Project America, led by John Koch. So the name RISC, Reduced Instruction Set Computer, did not come from IBM. That name actually came from Berkeley. But this 1974 processor within IBM is recognized as the first generation reduced instruction set computer. The main difference between a RISC computer and a CISC computer, complex instruction set computer, of course, is that with a RISC computer, operations generally transfer data from system memory first to the register file, and operations are from registers to registers, and of course, results are stored back in shared system memory. As you can see here, there's been several generations of power architecture. Of course, usually the architecture releases corresponded to microprocessor releases. Starting with the 32-bit processors, power server processors, Power 1 and Power 2, and then a series of products called Power PC that were leveraged by Apple and Motorola, amongst others. That effort then also led to an embedded version of the power architecture, which is called the Book E version of the architecture, which currently no new processors are being released on that branch of the architecture. So after the introduction of 64-bit power architecture after 1997, with the subsequent processors, the architecture has continued to grow from a few hundred instructions in the beginning, all the way up to 1,419 instructions with the most recent release of the architecture, that is implemented by the IBM Power 10 server processor. With the 3.0 version of the power architecture, the power architecture was brought under an open source framework, an open framework, and then later under the Linux Foundation. So the architecture is maintained by a working group, under the Linux Foundation, and implementations of the architecture that are compliant, can create processors, without encumbrance. In that sense, similar to the RISC V architecture. But of course, the power processors have as you can see here, a very long history, and a lot of code has been developed for the power architecture, and a lot of power systems have been developed as well. If we look at how the instruction set architecture is structured with respect to these compliant implementations, you see this tiered organization. Of course, it would be very difficult for an open project to implement the full 419 instruction ISA. So there is a progressive set of simplifications of the architecture that allows us a series of implementations, starting from a very simple implementation that just implements the scalar fixed point subset of the power architecture, which is only 129 instructions, to one that adds the floating point and is 214 instructions, and then an extension that introduces the subset that you would need for the Linux operating system, or rather, that Linux releases for Power soon. And that one, that subset is 962 instructions. And then AIX is the IBM Unix version. And that one requires yet a larger set of instructions, and then ultimately the full 3.1 ISA. So, someone who wants to implement an open core and fall under the open power license, which makes that free to do, has to pick one of these compliant subset and then ensure that the core indeed is compliant. This chart shows you in a little bit more detail, and I'm not going to go through each of the instructions, how this is structured. So the scalar fixed point subset and scalar and floating point are pretty obvious. For the Linux subset, there's a requirement for little endian mode, and adding support for the nested radix translation, as well as the SIMD instructions, and 64-bit mode. In the AIX subset, there is a number of other instructions that are being added, as well as big endian for 64-bit is a requirement there, as well as some of the special instructions, for example, for broadcast TLB invalidate entry instructions. And then there are a number of instruction types that are always optional. So any implementation is not required to implement those, and those are listed on top here. Perhaps one of the ones that you might have heard of is the matrix math assist, which is a new feature that was implemented on the Power 10 processor, basically doing tensor operations and adding those to the instruction set. And then, and this was done specifically in light of making an open architecture and encouraging innovation, while at the same time ensuring that the software base would have a foundation to work with, that where they could assume that those instructions were present. So there is the opcode space is organized in such a way that people who do their own implementations of this architecture have the ability to add instructions of their own design. And people who do so are very much encouraged to bring their ideas to this instruction set architecture workgroup, so that they can be considered for future releases of the instruction set architecture. Because of course, an instruction set architecture is really only effective if a community can assume a common set of instructions and design infrastructure like compilers, etc., operating systems to that common set. But again, that desire for a common set that is rigorously maintained has to be balanced with desire to enable innovation and new ideas, and that's why a part of the instruction set was carved out to allow people to add their own new instructions to the architecture. Next, I'll talk a little bit about the cores. So the first core that I'll mention, and I'll be very brief about this one because I know that this core is going to feature very heavily in this class, and therefore, I don't want to go too deep because I'm sure subsequent speakers will spend a lot more time going through the details of this core, and I assume you're going to learn how to actually build this core yourself on an FPGA. So the microwatt core, as the name suggests, is a really tiny power core. It implements the smallest subset of the instruction set architecture, the scalar subset. It's written in VHDL, and it can be simulated with the GHDL open source simulation infrastructure. And it can be synthesized with open source tools as well. And of course, as an open design, it's available, for use at GitHub.com. It was initiated by Anton Blanchard. So you can find it under GitHub.com, Anton Blanchard microwatt. It is quite a simple core. It is a pipeline design, but a small number of stages, and you see that on the right. So the ICAS and fetch stages are followed by 2 decode stages, an execution stage, and a write-back stage. And it's a single issue in order architecture. The intent here is to create an architecture that is compliant, but at the same time simple and easy to understand. And the project includes, besides the core, some other open infrastructure for a UART DRAM controller and Ethernet, so that you can create actually a small system and not just a core. It is very small, and actually efforts have been made, and you can see that in this graph, to keep it small. So after time that some new things were added, there was also an effort made to try and see if while maintaining the same functionality, the size of the design could be reduced. And 500 LUTs or lookup tables on an FPGA, 5,000 is indeed a remarkably small number. Now, this was as of May last year, or probably June. It's I think grown since then, but I think that also since then there has been yet another effort to reduce its size as well. It is quite an active project, so I collected this data today for this talk, and you see that the additions and deletions in the graph in the lower left is active until quite recently. You see the overall activity on the project on the top right, and some of the most heavy contributors to the project are listed here, and there's actually a total of, I think, 18 contributors to this project. And you know, there remains work to do, even though I think that these comments, I'm not sure that the comments are still completely up to date, because you know, a lot of work has been done on this core, and I haven't actually seen these comments being updated recently. Next, after the microwatt core, I'll talk in a little bit more detail about A2I and A2O. Actually, before I do that, I should mention there is another core that is also under the Anton Blanchard GitHub repository called ChiselWatt, which is a core somewhat similar to microwatt, but instead of VHDL, it's written in Chisel. So that is a somewhat higher level language than VHDL. So that is also an interesting project, but I'm not saying more about it here. So the A2I and A2O processors have also been contributed to open source by IBM, and you know, these are processors with a rich legacy. A2I was the processor core leveraged in the Blue Gene Q supercomputer, and you see a picture of a supercomputer there on the right. It's a core with 4 threads that are simultaneously executed in each core. So if you were to start Linux on that core, you'd see you know, four little penguins. And it's still an in-order core, and it's throughput optimized rather than single thread optimized. So I believe that these 4 threads actually sort of get instruction issue slots in alternating cycles. The other core is A2O, and that we'll talk about. And as the name suggests, A2I is an in-order design, and A2O is an out-of-order design with more emphasis on per thread performance. And that core supports 2 threads per core, and it's an out-of-order design with 2 threads per core, but optimized for single-threaded performance. So you know, these processors have been targeted for a variety of uses, ranging from supercomputers, as I mentioned, to edge computing, uses in the telecom industry, where power processors actually have been used widely, as well as automotive, where you know, power had a fairly rich presence. The platform vision for these A2 cores was that the A2I core was the initial design, followed by A2O. And the idea was to create a family of compatible, flexible, and modular processors that could be configured in a variety of ways. One of the ways in which these processors enabled configuration and specialization is with the AXU interface, not to be confused with the ARM-XC interface. So the AXU interface allows you to connect specialized units to the processor and allows the processor to issue instructions to that specialized unit. So it's instruction level integration of special purpose functions. And you know, besides being cores that have you know, good performance and are enabled for a variety of uses, they are also care is taken to ensure that you would be able to debug and work in the lab with these designs. So there's a lot of performance monitoring and debug facilities that are supported on these cores as well. And the design is quite scalable and modular. So you know, the building block approach allowed SoCs to be constructed in a variety of ways. If we look at the A2I processor, and this is a slide from a talk at the Open Power Summit in North America in 2020 by Bill Flynn. So it says open since June. Well, that was June of the prior year. The A2I core was implemented in 45 nanometer silicon on insulator technology. And it was initially developed for a network processor that I'll talk a little bit about in a bit. And that network processor was actually, in the end, not commercialized, but the core was then also used in the Blue Gene Q computer, as I already mentioned. And the architecture is the 64-bit Power ISA Book 3E, so it's that embedded branch of the architecture. And as you'll see in a bit, that actually means that the core as is not compliant to the Open Power ISA, even though the number of things that would need to be modified to make it so is not excessively large. As I mentioned, it's an in-order core with in-order dispatch execution and with an 8K branch history table and dynamic branch prediction. The caches are fairly small, you know, 16K four-way associative instruction cache, and a 16K 8-way associative data cache with 64 byte lines, cache line size. 512 by 4 entry translation leukocyte buffer, and 4 terabytes of physical addressability. That refers to the number of address bits that are actually interpreted. I mentioned the XU interface for tightly coupled coprocessors, and the design also has a microcode engine. And you can find this core at github.com Open Power Cores A2I. Bottom right, you see how big it was. One instance of that core was about 3 square millimeters in 45 nanometer technology. And of course, depending on the frequency that you ran it at, it was able to go up to 3 gigahertz, but at maybe a more optimal power performance point was 2.3 gigahertz and a little under a watt per core. And if you took that same core to a 7 nanometer technology, like the technology that the Power 10 processor was realized in, that core would be really tiny. It'd be only 0.17 square millimeter, and the frequency would go up, and that in that technology it would be fairly power performance optimal at 3 gigahertz and only 0.15 watt. So a really power efficient and small core. This slide shows you some of the details of that network processor, Power EN, that I referred to earlier. And you see that in this design, a number of these A2I cores, I think 16 of them, were combined with a number of other accelerators outside the core for things like regular expression, XML interpretation, or network acceleration. to create an SoC indeed intended for networking applications. So we go to the slide. So if you look at the microarchitecture here, I think I already covered most of these things, and actually won't have time to go through the architecture in too much detail. But this shows you how the processor was put together. And this slide gives you some more details of the architecture, and I included it for reference. I will not go through this slide in detail either. The A2I core was implemented on an FPGA, and this project is also available in that GitHub directory. And on a not the smallest FPGA, but not certainly not one of the biggest ones either. One instance of this core could be implemented using most of the resources of that FPGA, which was a Xilinx Vertex Altair Scale 3P FPGA in this particular case. So the processor itself in silicon is a 27F04 implementation. F04 means that if you take an inverter and you use it to drive 4 copies of itself, the delay of that inverter would be 1F04. So if you do that 27 times over, you would have a 27F04 cycle time. And as mentioned before, it's our ISA 2.06 book 3E. I mentioned some of the implementation details before. And then the last thing I'll mention here on this core is that the instruction architecture, because it was a ISA 2.06 core, would need some updates to become 3.0 or 3.1 compliant. And if you would want to go for the Linux subset, you would need to add radix translation, add some of the missing operations, remove some of the non-compliant ones, and make some other changes. It's not. It really isn't terribly far away from a compliant design. I also included this slide from Bill's presentation with some suggested projects that people could do to contribute to this open design, including, of course, the things to make it architecturally compliant, alternate FPGA implementations, adding accelerators, and other things. So the next core I'll talk about is the A2O processor core. So unlike the microwatt core and A2I, which were implemented in VHDL, the A2O core was implemented in Verilog. A2O is more focused on high-performance single-thread computing, which makes it more optimized for a different set of use cases, including those where latency matter, like autonomous driving, for example. It's again a book 3E version of the architecture, 2.07 in this case. And this core is a two-way simultaneous multi-threading core. Even though the back end of the pipe is, as well as the front end, is 4 wide, right? So, you can dispatch 2 instructions actually per thread per cycle. In this case, it's out of order dispatch and execution and a more sophisticated branch prediction unit. The caches are twice the size of the caches in the A2I, so these are 32 kilobyte instruction and data caches, still a 64 byte cache line, you know, also enhanced completion buffer and load store queues. TLB, I think, is similar in size as is the AXU interface. And this core has full support for both big and little endian byte ordering. So you know, if you're looking for a core with good single thread performance and support for these other features, A2O would be a good core to start from. Again, I won't go through the details of the microarchitecture, but I included this diagram for reference. You know, if you look back, you will see, I mentioned that in 7 nanometer, the A2I core would be, you know, quite small. I think it was 0.15 watt and some 0.17 square millimeter. This core is a little bit more than twice as big and a bit more than twice as power hungry compared to the A2I core. I think I've already mentioned the items actually on this slide. This core was also implemented on an FPGA, and on that same FPGA, they could only realize a one-threaded version of this core. So if you'd want to implement a full core, you would need a slightly bigger FPGA than the VU 3P that was used here. I think that is mentioned here. And there was also you know, 50 megahertz for an FPGA implementation of the core is something that one would certainly hope to improve on. Most of the FPGA projects that I have pursued now, those were from scratch design, so that's not that's easier than taking an existing design and mapping it to an FPGA. I usually shoot for something like 200 megahertz. As with the A2I core, very similar updates would be needed to be made to the ISA to make it compliant to the Linux subset. And here too, a similar list of suggested community activities. And then, you know, I think I should mention that in the case of the A2O core, a lot of the work to map it to the FPGA and make it available to open source was actually done by these three interns who worked at IBM for a summer before well before COVID. And I've included a number of slides with resources and a number of talks and presentations about A2I and A2O that may be of use to you should you decide to look at these cores. A number of these presentations actually also cover microwave. So then in the last few minutes here, before I leave time to take some questions, let me talk about OpenCAPI and FPGAs. So I think you will spend the majority of the next 40 hours working on processor cores, which you know extremely rewarding activity, I do believe. But working on accelerators is also very interesting and a lot of fun. My particular, having worked on accelerators or specialized processors, ever since the PlayStation 3 cell broadband engine, I strongly believe that in a good architecture, the accelerator has full access to the resources of the system, and in particular shares the same view of system memory with the host. So that requires a different kind of interface than the typical I/O interface, where the accelerator is only able to access certain regions of memory or pages that are pinned by the operating system, and that where the I/O translation has been set up in such a way that the accelerator or attached device can access memory there. And this is really quite limiting. One extreme example that I can give is, imagine that you might want to create an accelerator that walks a graph in the host virtual memory, which, by the way, in the case of power architecture, it's effective addressing, because power is a two-level address translation. We translate from effective to virtual to real. But let me just call it virtual addressing. So every time that accelerator would want to dereference a pointer to go to the next node in the graph, it would actually need help from the operating system, because it would not have direct access to all of system memory. And the operating system would have to take the pointer that the accelerator provides, dereference it, translate it to a real address, copy the data to a place that the accelerator can access, pin the page so that the page is always accessible with that different address set up for the accelerator. The accelerator would do its work. It would place the results in another buffer or pin location, and then again the operating system would be required to assist in bringing that data back to the user process that requested it. And this easily requires thousands of instructions, and in the order of 10 or more microseconds of time in order for the accelerator to do this. And that means that for something that requires frequent dereferencing of virtual addresses, pointers, using an accelerator is completely impractical. And therefore you've seen even powerful accelerators like GPUs work in a mode where typically there is an explicit data copy phase from the host to the accelerator before the accelerator can do its work. And that leads to extra copy operations. It leads to excessive operating system involvement, and it adds latency and reduces performance, or limits the application space. So in Power 8 and Power 9, IBM actually worked with NVIDIA on an interface that was leveraged the same physical layers and was conceptually similar to the OpenCAPI interface, to be able to use the GPUs in a shared address mouse mode with the host, again avoiding all these copy operations. So like OpenPower ISA, OpenCAPI is an open standard and maintained by a work group at opencapi.org. So I mentioned there would be this class. It's called Accelerating Big Data Analytics Applications with FPGAs and OpenCAPI. It's a little bit, even though we will give background and the information you need to build your own FPGAs, it's a little bit more targeted at people that come in with a software background and not necessarily much of a hardware background. But everything is there for people who want to dive deeper into the FPGA designs and create their own accelerators. And I've included a number of links. So the web pages here and playlists, etc., are still incomplete. As the course will only start towards the end of this month, and then material will be added gradually as the course progresses. But a number of the course modules are already available. So with that, let me stop and ask and I guess return to Dr. Trivedi and ask if there are any questions. I'm looking at the Q&A channel. I don't see questions there.
Hello. Yeah, dear participants, can you hear me? So we
Yes,
request you.
I hear you, Froza. Thank you.
Yeah, okay, sir. So we request the participants, if you have any queries, then you can put it on in the Q&A section. We will be there to answer you all. Thank you.
Okay, there's a good question. Is Chisel meant for transaction level modeling of processors? I would say, not sure if I'm interpreting the question correctly, but the answer is probably no. It is actually a description of a processor that you can compile, to an actual implementation on an FPGA, for example. So in that sense, it's similar to VHDL, but at a just in a higher level language. Now, of course, both the VHDL and Chisel design, can be simulated, and that can be done, typically in a, you might simulate it in a cycle based simulator, but sometimes, especially if you're building it into SoCs that have asynchronous components into them, transaction type simulation may also be possible. The question is, can we use open power in a multimedia enabled embedded system? So I would say yes. So some of the extensions to the power instruction set architecture are the media extensions, the VMX instructions and VSX instructions that accelerate a number of different things, but including multimedia operations. So yes, the instruction set, again, depending on which level of the instruction set you implement, includes those types of instruction. And yes, the PowerPoint will be available in that Google folder, that Google Docs drive that I hope all of you will have access to. So I've been reading these questions from the Q&A channel, so feel free to shoot me any other questions you might have.
Is there any other question in the Q&A section? I think so. There are no more questions, right?
I think that was it. So then I guess we can end just a few minutes early. Thank you, Veronica.
Yeah, thank you, sir. So thank you, sir, for such an informative talk. We are already getting response from the participants that they have enjoyed the session. So thank you, sir, for such a wonderful talk and joining us today for this session. So with this, we are coming to the end of the first session of day one. Ganesh, sir, would you like to say a few words, sir? Ganesh, sir? I think so, sir is muted. Okay, thank you, sir. So with this, we are coming to the end of the first session. So dear participant, we can start this session in another 2 to 3 minutes, the next session for day one. So thank you, sir, for joining us. And we are really happy on behalf of all the academies, sir. We give the vote of thanks to you, sir.
My pleasure, and have a good rest of your day, and good luck to everybody with this course. Thank you so much. Bye-bye.
Yeah, thank you, sir. Thank you. Thank you. This is again an announcement for all the participants. We have noticed that few of the participants has not registered by their registered email ID. So you can, in the meantime, when we are starting the next session, you can please sign out and join by your registered email ID. Your registered email ID will only be used for marking the attendance. So please join by using your registered email ID. Thank you. Ms. Aditi, may I request you to please give the presenter right to Vinod, sir?
Yes, sure. Presenter right is provided to Vinod, sir. Thank you.
Thank you, Ms. Aditi. Good morning, Vinod, sir. Sir, we have given you the presenter right, so you may share your screen, sir. Sir, in another 1 minute, we will be starting the session.
Sure, thank you.
Good morning, sir. So your slides are visible, sir.
Thank you.
Thank you, sir. So welcome back, participants. We are starting the second session for day 1. The second session will be delivered by Mr. Vinod Bhusa, sir. Vinod Bhusa, sir, is going to cover the topic that is power ISA versus RISC-V comparison. Vinod Bhusa, sir, is a senior engineer at IBM Systems and Power ISI architecture. As an expert, he developed tool for the post-silicon validation, and he has developed the technical talks, many technical talks about the Power ISA in open power IBM Power workshops and conferences. With this small introduction, we would like to invite Vinod sir in this platform to please start with the session. Vinod sir, over to you, sir.
Hey, thanks for the introduction. Good morning.
Yeah, thank you, sir. Good morning, sir.
Good morning. Okay, so I think after the Peter C session about open power ISA, I would go after it into little more internals, and then this session should help. If we go and study open ISA, it should help us to get educated, and it should help us to learn more from the instruction set architecture. So the general overview of my talk, basically in instruction set architecture, there are 3 books involved in the instruction set architecture. So I would go and give a high level overview, and then discuss a little bit about memory modeling, memory model of the computer hardware of power implementation, like weak ordering versus strong ordering, then about sync instructions, atomicity, then reservation instructions, and also touch upon the interrupts. So as we all know, power architecture is open, and then we have a compliant instruction set architecture, and previous presenter also has presented it. But what does the power mean? What is the full form of power? Power means power optimization with enhanced RISC. So this is the full form of power. Going to book 1. So book 1 contains everything which an application programmer needs. What all instructions are present, how to access registers, what different kind of units are present, and then their corresponding instructions and registers. That is what book 1 teaches us in instruction set architecture. So it would be like branches, load and store instructions. And when it comes to arithmetic ops, in case of RISC architecture, arithmetic ops are only between register to register. Memory is not involved. And then we have fixed point unit, binary floating point, decimal floating point, vector, and vector scalar instructions and registers. So I'll go over these things. Then going to the special purpose registers, when we are working on different instructions and instructions corresponding to different units. So we have a condition register. Condition register is, when you compare something, condition register gets set, and it is used by a lot of fixed point units, reservation instructions, and also even floating point instructions, and different condition register field is set. I will also go over it a few slides later. Then we have count register, target address register, link register, fixed point exception register, floating point status and control register, vector status and control register. So these are all different SPRs, which we have to be aware when we are working on power instruction set architecture. Like for fixed point exception register, this is corresponding to fixed point unit. So if there is any exception like overflow, underflow, those kind of exception, you get the result in this register. Similarly, there is a floating point status and control register. So in this register, you can set what rounding mode you want, whether you want to round to infinity, round to zero, all of those kind of stuff, and whether you want to take an exception, whether when a number is not a number, in all the IEEE standard stuff which we can do. So floating point status and control register is where you get the status, and you can also control how you want to work on floating point numbers. Similarly, VSCR is vector status and control register. When you are working on vector instructions similar to FPSCR, you can control what do you want to do, how do you want to control the numbers you are getting, how you want to operate on them, and the status of those instructions. Moving on to branches. So there are different kind of branches. Relative branches would be, as we would if you guys have programmed in assembly, you would be aware of this. So relative branches would be, you want to branch a few instructions later, so you can tell, I want to branch to 4 instructions from the current instruction, or I want to branch to a label would in turn become a relative branch. In case of how the compiler codes it, they can also maybe make it absolute branch, but generally it would be a relative branch. So relative branch, but then it would have an offset. You cannot branch more than a few instructions. There would be a limit, because the relative offset which you want to branch to, it would be coded as part of the instruction. So how many ever bits are allocated in the instruction for the relative offset, you cannot overflow that relative offset. So relative branches, relative branches would be the easiest way to code, but then there would be a restriction of how many instructions you could branch off to from the offset. Then absolute branch would be, it's not relative, you will branch off to a specific address, and then you will have your instructions there. That would be absolute branch. Then there are other kind of branches, like main branch would be using the link register. So this kind of branches are mainly used in our function calls. When we make a new function call or a subroutine call, we would we would load the link register and branch off to the link register. And it also would be used when we are returning back from the branches. Then we also have some conditional branches, like, you branch only when a particular condition is met. So those would be starting with mnemonic BC, and then the places these could be used, if we map to our programming languages, would be for loop or while loop, all of these loops where you would loop until a verb in a for loop until some certain number is reached. When you increment some number, like maybe I 0 to 50, till 50, you will branch, but you have a condition only till 50 you want to branch. After that, you don't want to branch. So those would be conditional branches. So they would depend upon, so internally branch condition for loops will be implemented using branch condition, and they can use different registers how they want to implement. One of the register could be CTR, count register. So whatever we have in the for loop or while loop, how many ever times we would want to loop, they can load the count register CTR, and then they'll keep decrementing as the loop as we loop through. And whenever CTR reaches 0, then you are done with your branching, and then you would not loop anymore on it. So there are different, there are pivot field in this instruction, which will help us to, determine how we want to branch. Then there is another field also in this instruction called AT. AT is a hint. So you can also give a hint whether, generally this branch will be taken or not. So if you don't give any hint, the value would be 0, 0, 0, 1 is reserved. So either it should be 0, 0 or 1, 0 or 1, 1. So 1, 0 tells, branch is very likely not to be taken. And 1, 1 is branch is very likely to be taken. So microarchitecture will use this information to decide whether this branch is taken or not, and he can speculatively execute the instructions which are there after the branch, or he has to, or a branch taken path or not branch not taken path. So hardware microarchitecture hardware will use this feature to speculatively execute the instructions, or even prefetch the instructions. From where does he has to prefetch the instruction? Should be branch taken path or branch not taken path. Okay, so I touched upon this earlier. So condition register gets set whenever you do some kind of a comparison. So this is a 32-bit wide register. Basically there are 8 4-bit fields in this register. They are called CR0 to CR7. So CR0, the first 4-bit field, this will be implicitly updated by any fixed point instruction which has a dot form. So whenever there is an instruction with a fixed point instruction with dot, it basically, we are telling, you need to update the CR0 after you execute this instruction. So all these instructions will update the CR0, and then one of the example would be stux. Stux is a like a store with a reservation. So if you have a reservation, then you will store, and then if the stux is successful or not is recorded in CR0. It's a dot form instruction, and the success of this instruction is recorded in CR0. Similarly, CR1 is implicitly updated by all floating point dot instructions. So those would include binary floating point, decimal floating point, and vector scalar instructions. Then CR6 is updated by VMX instructions with the dot form. All of the VMX would use CR6. Then other CR fields, they would be used by compare instructions. So there are compare instructions where you can compare the registers, and they are also used by when you want to move something to CR itself, like move to CR. You can also specify which field you want to move. So those instructions also use the other CR fields. So there are some instructions where you can modify the CR, like CR and, CR NAND, CR or, CR NOR. So we all know the AND, NAND, or, NOR. So you can manipulate the CR, what the value is there in the CR by using these instructions. And other way to modify the value in the CR would be, you can do a move to CR. And if you want to know what the value is there in the CR, you can also do a move from CR. And if you want to only read a particular field in CR, then you would do move from, like a MFOCRF. So that will only move a particular field from the CR. Similarly, you can also move to only a particular field in the CR using, move to OCRF. So these condition register, these bits also would be used by branches actually. So whenever you are branching, you do a comparison when a particular value is there in the condition register, and you can tell, you will branch depending upon what the value is there in the condition register. we touched upon the count register. So branch can be, like a branch can happen over the count register, like a example of a for loop where, the count decrements and then you keep branching until the counter is 0. And other way the count register is used is also, you whatever is there in the address in the count register, you can branch to that address. The basically count register is used as a target address. That would be another way to use count register. Then there is also a register called target address register. It's somewhat similar to count register, but here, there is no decrement or anything. This register just holds what is the target address, and you will just branch. You can use that register to branch off to that address, branch to target address register. Then there is a link register. This is similar to count and target address register, where you can branch off to link register, but then it has much more usage, like I touched upon earlier. All the subroutine calls, they use the link register, whether to make a call or you want to return from a call. So there are instructions when, there is a branch and a link instruction, which basically whenever you make a branch, then, the next address of that instruction would be basically loaded in link register. So what you would do is whenever you do a return, as the link register is already loaded, he knows where he has come from. So he will branch off to the location from where he has come from. Fixed point unit. So fixed point unit, there are different operations which happen in fixed point unit, fixed point instructions. So the operations are, like a register to register. So it could be and, or, subtract, multiply, divide, like rotate, shift, compare, select. So these are all different kind of instructions if we take any high level language like C or any language, we do all of these operations. So internally, all of them would be converted into assembly instructions like add, subtract, multiply, divide, and all of this. And these would be operated upon, these instructions would be dispatched to fixed point unit, and fixed point unit would be who would be executing these instructions. Then there is an instruction called trap. Trap is an instruction which will generate an interrupt. You can ask a program, to trap if you think that is something which should not be done. Like there is some condition, like if you expect some variable to not have a value 0, and you want to trap whenever the value is 0. So here you get a program interrupt, and then that's one way to trap the processor. So there is an instruction called trap. Then there is an instruction called DARN. So this will generate a random number for us. So this is very important. We know that whenever we are running on hardware, we want to do some stuff where we require a random number to do something. Like suppose you want a program where every time he runs a particular piece of the code, you want to give a different input to that piece of code. One way is, you have to generate a random number using some software mechanisms, and then you will feed that number into these routines so that it takes a different path and you get a different results. So here hardware is helping us to get a random number. So every time you execute this instruction, you get a new random number, and this you can feed to the software where you want the input as a random number. Then you also have instructions where you can do a move to and move from a GPR to VSR. VSR would be, I would touch upon it again, vector scalar registers. So you can move stuff from GPR to VSR to and fro. After fixed point unit, we have floating point unit. So floating point unit, IBM processors power instruction set of compliance with the IEEE standard. So they implement all the floating point instructions as per the IEEE standard. So we have different floating point units. Actually, one is BFP called binary floating point. So here different kind of input numbers are supported. One is single precision and other is double precision. So in case of single precision, you have the operands as 32-bit operands, and each register will have one operand, one operand. And in case of double precision, the operands would be 64-bit operands, and each FPR can have one double precision operand. And all the binary floating point instructions begin with the letter F. So when you go through the instruction set architecture, it's easy to know, if it's a BFP or not. So if you see it starts with F, it's a binary floating point instruction. And then there are 32 floating point registers, which can be used to perform this floating point operations. And BFP is a single instruction, and a single data. Then we have VMX or vector instructions. Here, the only single precision numbers are supported, and 32-bit operands, and there are 4 operands per register, and all these registers, all these instructions start with letter V, and there are 32 VRs, and each VR is basically 128-bit. So that's the reason you have 32-bit if you have 32-bit operands, there are 4 operands per VR. Then the next unit is a decimal floating point unit, and even this is a single instruction, single data, and VMX is single instruction, multiple data. As we saw that we have 4 operands, so it's multiple data. So in case of DFP, it's a single instruction, single data. Here, different kind of operands which are supported would be 32-bit, 64-bit, 128-bit operands. So in case of 128-bit operands, it's actually uses a pair of floating point registers. So it will use even odd pair consecutive registers to even register, and then followed by an odd register. Then you would get 128-bit. Otherwise, whenever 32-bit or 64-bit operands are used, the one floating point register is used. And all DFP instructions begin with the letter D. And DFP instructions operate on the 32 floating point registers which we have. And there are some quad word floating point DFP instructions, like which use this 128-bit instruction, 128-bit operands. There, the instructions start with letter Q. And then there is another unit called vector scalar extension, and vector scalar instruction extension unit is a SIMD, single instruction, multiple data. And here a single precision and double precision both are supported. And here the registers are 128-bit registers, and there are 64 VSRs. And whenever there is a single precision, he takes 4 32-bit operands, and in case of double precision, he takes 2 64-bit operands as input, and all these instructions begin with letter X. Okay, so till here, it's more of what all units are there, what kind of instructions are there, what kind of registers are there, and that is mainly book 1 at an high level. And then next would be, Power ISA virtual environment architecture, and this is something where operating system is what deals with this content. So here, mainly the storage model is discussed, and then their attributes, and then the instructions which manage the shared storage. So there are different kind of storage model, like it can be weakly ordered or strong access ordering. Then there is the caches, and how are they, what are their attributes, whether it's a write through or cache inhibited or memory coherent or your memory is guarded. And then there are cache management instructions. And when memory is accessed by different instructions, whether it's accessed on the same thread or a different thread, or you have to synchronize those accesses. So the help from the hardware to do that. And then I would also touch upon sync and EIO instructions, then atomic access instructions. So when it comes to memory model, so generally processors implement weakly ordered. So what does weakly ordered mean? So when there are a set of instructions, like there are 100 instructions which are there, and then there are a lot of load stores. So access to different bytes can happen in any order. By this, what I mean is, suppose there is a store which is like first instruction is doing a store, and maybe 10th instruction is doing store, like a first instruction is doing store to location A, 10th instruction is doing store to B. So the access to location A and B need not be in programming order. So access to location B, which is accessed by 10th instruction, that access can happen before the access to location A by first instruction. So that's the reason, this called weakly ordered, and access to different bytes can appear in any order. And that's what is called weakly ordered. But then there is a hardware support. See, if those locations are not in any way connected, then the program is okay to access them in any order. So those two are completely different locations, and they are not, like, your program doesn't depend on the values of those two locations. The logic is not in any way connected. Then it's if it's weakly ordered, and then you don't have a problem, and then it allows the hardware to use this feature microarchitecturally to give the best results, like do the accesses very fast, program to be very fast, and you get the performance out of it. But there would be a problem if there is logic in the code, the software code which is using these locations. There is some interdependency how the code is using. They want like the first instruction access, whatever happens, they want that to happen before the next instruction access. Then there is a support given by hardware. They can use instructions like EIO or sync instructions. Basically, what if there is a sync instruction, he will order these accesses which happen. I'll again touch upon it. Then other part to weakly ordered is if the access is happening to the same location, like when we do a store to A and a store to B, and this A and B are actually overlapping locations, or in case they are exactly same locations, like I am actually accessing the 0th byte of a certain page in both of these accesses, then the accesses should be like a sequentially execution model, like it should be in programming order, and you don't require any string sync instructions here. So what hardware does in weakly ordered is only when the locations are not overlapping, or only when the locations are not same, then he would not guarantee us the order in which these accesses can happen. But whenever the locations are same, then hardware does the accesses in programming order. And if you want the accesses to be in order of those which are also not same, the locations are not same, hardware does provide the support. We can use the sync instructions. Okay, memory attributes. So there are different memory attributes that are used by hardware. They're basically called WIMG in short, like W for write through, I for cache inhibited, M for memory core, and G for guarded. So what does write through does? So if the value is one, whatever access happens to the cache, it's immediately returned to memory. That's what is called write through. But if it is 0, then writes to cacheable memory are not immediately returned to memory. So what cache we know is like the buffer of the memory, which is on the hardware, which is not far off like memory, where you can access very quickly. So this write through will decide how we want it to be. So obviously, if you want to, if you set the write through to 1, you are basically, writing everything, whatever is there in the caches to memory immediately. So you would have a performance impact on it. And if you are using a 0, he will only do a write whenever it's required. And when is it required? Suppose the same location is being accessed by some other thread or some other core. He knows that who has the recent copy, and then that particular thread from that cache, it is returned back to the memory. So write through, you can gain performance when you have 0. But then you have some certain application or certain way where you think 1 is what you want. You cannot live with not writing to the memory immediately, or that this particular location, whichever is being accessed, would be accessed by a lot of threads, lot of cores simultaneously and very fast. Then you can go with write through, so that it's really written off to memory and others can access it. Then the next attribute is cache inhibited. So cache inhibited is something where some accesses where you if cache inhibited is 0, you are telling you can cache those locations. Those are cacheable. And if it is 1, you don't want to cache those locations. And generally, IO is where it goes into cache inhibited wherever IO is involved. So you generally don't cache it. Like if there is an MMIO location on some adapter or some network card or PCI card, then you don't want to cache it, because the register values or the memory map values will keep changing, and that's where cache inhibited is used. And then memory coherent. This is like whether the memory is kept coherent by hardware or is not kept by hardware. And this is like a coherency which is there. And these days we talk about coherency with accelerators too, whether you want to keep the accelerators memory when whatever is accessed by accelerator and hardware is coherent. Generally, IO memory is not coherent. You don't keep it coherent. But then we have a CAPI hardware where we have a coherent interface, and that's innovation from IBM, which is present. And then Peter of C also has touched upon it. You can work on those accelerators, CAPI, where the memory is kept coherent. Otherwise, generally all the memory is kept coherent other than IO hardware. But if you want the IO part also be coherent, one way would be go through CAPI. But it depends on what all you can do. But that would be one option. Then there's another attribute called guarded memory. So guarded memory, you can set this attribute to 1. What happens is all the accesses to that particular location would be in order, and then they wouldn't speculate. But if you set this value to 0, then non-overlapping accesses are permitted to occur in any order, and then the memory is speculatively accessed. Okay, then we have LUX and STUX. These are reservation instructions. As we know, when we write programs, there will be critical section. We need some location to be accessed only by one thread, though it's a shared memory. So that's where these instructions are used. So we may be writing a semaphore or a mutex, but internally on power hardware, what it gets converted to these instructions. So LUX is a load and reserve, and there are different granularity of these instructions. You can do a load and reserve on a byte, half word, word, double word, quad word, and then this reservation gets set. And then whenever this one particular thread executes this instruction, you get the reservation set. And once the reservation gets set, when you do a store, if your thread has the reservation, then that store would be successful. that would be store conditional, and then and even in store conditional you have all those granularity of instructions like byte, half word, word, double word, quad word. And then store, when you do a store, it's like when it's you have still the reservation, because all the threads are trying to do a store here. They try to do a load and reserve, and then also a store if whoever gets the reservation. It's like you're looping like on a semaphore or a mutex. So that's the situation here. And whenever store is successful, your CR0 gets updated, and that's how you know that you are successful. You got the access. You can go ahead. And if you did not get, then you will continue this loop of go back and do a load, then get a reservation, and then do a store. Then we have this sync instruction. As I said, when you want to basically see that all the accesses, whichever we want to be performed in a certain order, we can achieve that by using a sync. So it's like a barrier. So if there is a sync, any accesses which are there after sync would be only performed after all the accesses which are there before sync are completed. And sync instruction is also it does this this kind of barrier part for both cacheable and non-cacheable accesses also. Something if you are accessing even the IO, this sync instruction would take care that all the preceding load stores are completed before the ones which are after the sync. And this sync can be performed between load and load, load and store, store and load, and store and store, all the four combinations. Okay, moving on to interrupts. We know that we have a different kind of interrupts which are present, and interrupts is one way where instead of busy looping on something, you take an interrupt, and that's how you get the performance on the hardware. So there are different kind of interrupts. There could be synchronous, asynchronous. So asynchronous would be something where you are doing something on your program, you get an unrelated interrupt. That would be asynchronous. That means like whatever you are doing at that particular instruction is executing, it's not related to that, and you get an interrupt. It could be like a decrementer who wants to do some process scheduling, or it could be an external interrupt or some doorbell, and all of those kind of interrupts. Whereas synchronous interrupts are something which happens due to the current instruction which you are executing. So if this instruction is accessing some unaligned memory, or this instruction, when it is accessing some memory, it doesn't have a translation to that the location he is trying to access. So he takes an interrupt, then application program may be executing some instruction, but he doesn't have a translation to a particular real address he wants to access, like a load or store. Then he would get an interrupt. Then operating system would go and install translation, and then it would come back, and then application program would be able to access. So those would be synchronous interrupts. And in power hardware, whenever interrupts happen, there are a few registers where it would be important, like SRR0 and SRR1. And if it's a normal interrupt, if it's an hypervisor interrupt, then it would be HSRR0 and HSRR1. So SRR0 would contain the effective address from where the interrupt is generated. So suppose you get a page fault interrupt. When you go to page fault interrupt, if you want to know, from where you have come, SRR0 is the one which contains the address from where you have come. And similarly, there is an MSR register called machine status register. And whenever there is an interrupt at that particular point, whatever was the machine state register, that value is present in SRR1 register, which can be accessed by the interrupt handler. And MSR basically tells, what is the machine state, whether, translation is on, translation is off, whether the hardware runs Little Indian, Big Indian. In case of power hardware, generally both the modes are supported, Little Indian, Big Indian, but it may depend upon the operating system you are running but otherwise from hardware perspective, both the modes are supported. And similar different stuff like that. All the status register of the hardware would be present on the MSR. And then there are two instructions. Like in case of operating system, there is an instruction called RFID. Basically, it's an instruction you execute when you want to return from the interrupt handler, and then there is an HRFID. So whenever RFID is executed, what happens is whatever is there in SRR0, that gets the program would jump to whatever value is there in the SRR0. And similarly, whatever is there in SRR1, that value is basically returned into MSR whenever RFID is done. Similarly, when HRFID is done. So that's a way to give control back. Like you got a page fault interrupt and you want to return from the page fault interrupt, the place you want to return back would be present in SRR0 when you are doing an RFID. And when RFID is performed by a hardware, he will return back to the instruction from where page fault has occurred. And SRR0 to program counter is what one can imagine it as. So I have briefly touched upon the open instruction set architecture. It should help when we go through the open ISA and then go through different books and understand the instructions registers. Then I will briefly touch upon RISC-V. So RISC-V architecture these days is used, predominantly. Even RISC-V is open source. There are different, word lengths which are supported in RISC-V. One is RV32, RV64, RV128. When it comes to RV32 and RV64, there are incremental instruction set architecture, but mainly RV32 and 64, there are a lot of instruction set architecture which is frozen. But when it comes to RV128 is something which is still being developed. So the instruction set architecture is not frozen. So there is still, some improvements being done, things are being added, and this is all open source. And there are, 32 general purpose registers in RISC, and the instructions are variable instruction length. So each instruction length is not constant. And there are three privilege modes. One is machine mode, M mode it's called. Then there is a supervisor mode, and then there is a user mode, U mode. U mode would be something like a like application programs run. Supervisor mode would be operating system. M mode would be something like a firmware kind of a code which would run. And then there is a control and status registers for each of these privilege modes, like M mode, supervisor mode, and user mode. And in RISC-V, actually, there is like a different kind of ISA extensions. So, it depends on what one wants to implement in their processor. So they need not have everything. So they have subsets, or they're called extensions. And standard naming convention is RV stands for RISC-V. Then 32, 64, 128 tells their machine word length or what is the register length. And then they have different kind of extensions, and some of them have given here. I stands for integer, then M stands for you have integer multiplication and division. A stands for there is atomics also present. F is a floating point, single precision floating point. D is double precision floating point. G is general purpose. So whatever is there till now, I, M, A, F, D, would be general purpose. So somebody may, if they take all of that, there would be, you can just use G, and you would be conveying the meaning to them. And then C is 16-bit compression instructions. Then H is if there is a hypervisor extension also, and V is vector instruction. Then coming to RISC-V and open instruction set architecture, RISC-V is a free and open ISA, and it's enabling, you know, a lot of processor innovation. And then there is an open standard collaboration which is happening. And if you want to learn more about you know, RISC-V, this would be the site you know, where it would be accessible. And similarly, OpenPOWER ISA is a very high performance instruction set architecture. A lot of servers are implemented based on OpenPOWER ISA, as my previous speaker has given a chart when, you know, which processor like P7, P8, P9, and as you all know, P9 is a hardware which is working on a supercomputer. There are supercomputers based on P9 hardware. So it's a very high performance instruction set architecture. And then there is this instruction set architecture is open source and it's accessible, you know, in the following site. And there is a lot of information on this OpenPOWER Foundation ARC site if we want to know more about it. Okay, so I think this is all I wanted to cover. So I think we have some time. I wanted to have some time at the end if there are any questions. So I'm open to questions. Okay, so sync instruction. So sync instruction, suppose there are like in a program, we have a lot of loads, stores. There are a lot of loads and store instructions, and the way we are using the results of the load and store instructions. Suppose there is some dependency. Suppose I am loading a particular variable called X, and if I want to use that X to calculate the result in some operation, suppose I'm doing a multiplication on X or something of that sort, or a division, or I'm using it as a parameter to get a new value called Y, but then there is some other variable also Y is dependent upon, like you know, and there is an interdependency between these two locations which can be accessed. So if you do a sync instruction in between, you know, you want two instructions. Suppose you want location A and location B to be accessed in order. After location A is accessed, only then you want to access location B, then you can use a sync instruction in between. And the reason sync instruction is required in between is these locations A and B are not same locations. You are not accessing the same location, due to which you need a sync instruction. Because what hardware does is whenever the locations are not same locations or not overlapping locations, hardware does some optimization. He does you know, speculative access of the memory caches, so that, you know, you get a better performance. So what he does is he can access location B earlier to location A. But due to whatever reasons in our program, if we are writing code such that, you know, only after reading A, you have to read B location, then you can place a sync instruction in between, so that, you know, your access happens, hardware accesses those locations as per your requirement, whatever program wants to do. And sync instruction can be done between a load and store, store and store, you know, all those four combinations. And this instruction also does this ordering between cacheable memory and non-cacheable memory. Like if you are even doing an MMIO or an IO access, even there, if there is a load and store, there is some load and store to cacheable memory, and there is some load or store to non-cacheable memory. Even then the sync orders those, access of those locations. So that's about sync. Then coming to chord word DFT instructions, that is true. All of them it's not end, they start with Q. Okay, from where to start if we need to study RISC-V? The RISC-V, the site I have mentioned, that would be a good place to start. That's an official site. Actually, riscv.arc would be the site. And if you want the instruction set architecture, then it would be riscv.arc technical and then, specifications. This would be the site. Okay, I think thanks. I think we have a few minutes left, but I don't think so there are any questions. Thanks for this opportunity. Then I think you guys can take over.
Sir, there are some questions in the Q&A window.
I answered them. Are there any more? Okay, on slide 18, how many letters minimum or maximum need to write in the end? Like RV32 GI. No, you wouldn't write GI because G means general purpose. So integer is already present in that. So IMAFD, right? So you are telling G to tell that all of this instruction set architecture is already present. So you already have integer, you already have multiplication and division, you have atomics, you have floating point, you have double pressure. Then you want to call it as G. So G can be used with anything like C, H, V, which are not present on the top. I don't think so. These are like how many letters are there, like min or max, because this is basically, you are telling which instruction set architecture extension you are using. So if you are using IMAFD, you can use it. Actually, you can use G instead of IMAFD because you need not use so many letters. That site which I have mentioned for RISC-V would be the site from where we can start off. That's where the architecture is defined, and ISA is the place where you need to start off for knowing the architecture. So riscv.arc technical specifications, this would be the site which will give you the ISA. And in general, riscv.arc, the parent site itself has a lot of information about RISC-V. RISC-V, sorry. The weakly ordered memory model, is it the OS that controls the access or the hardware? So it's like the hardware which does this. Hardware will decide whether the hardware is weakly ordered or whether it is strongly ordered. So some processors give you an option to be strongly ordered, but by default, a lot of processors go for weakly ordered modeling, memory model. Only some processors will do a strongly access order. Some processors won't even implement strongly access order. And when they implement strongly access order, they give the programmer an option to use the strongly access order. So in as strongly access order, as the word means, the way the accesses are done, they are ordered like a programming order. You will order the location, the loads and stores, and you would lose on the performance. But then you need not use sync and all of these instructions, but then you would lose on the performance. So but for performance, almost all the processors implement weakly ordered memory model, and it's the hardware which it implements and not the OS that controls. But if hardware is giving an option for strongly access order, there would be an provision. It would be available for AP for you application programmer, but obviously he has to go through OS and hypervisor to do it. Like in case of some processors, they may give the strongly access order provision through the translation. You can tell through the translation, this particular memory location which I'm accessing, I want it to be strongly access order. But you will lose on performance. Weakly ordered, where you will gain performance. So it's simple, when two locations are not actually anyway dependent, and in our program, you can allow them be accessed in any order you want, and that's how you can get performance. And most of the times, the different locations we access in our instruction stream or our application program would obviously not be dependent. Only few locations would be dependent. And if those could be, and generally if you are writing an high level language, compiler will take care of it. He will apply syncs and stuff like that. But it depends whether you are doing some IO programming or a device driver programming or certain programming where you have inserted assembly instructions. Then obviously we have to take care, the programmer has to take care of the memory model. So in conclusion, the weakly ordered is done by the hardware, and processors may give an option to do strongly access order, and that would be through operating system, but the main decision is from the hardware. Access to a variable A and then B, which is 10 instructions apart, who decides whether to access as variable B or not. So see, we know that in this server processors, what happens is there are a lot of instructions which are prefetched, and then you would be actually speculatively accessing these instructions. One easy way is, suppose there is a branch instruction. You know that for a branch instruction there is a branch taken path and not taken path, and till the hardware really goes and executes that branch instruction, we do not know whether we would take a branch taken path or not taken path. But in microarchitecture, in hardware, there are a lot of algorithms which predict whether the branch will be taken or not taken. So depending upon the prediction, hardware will go and do a prefetch of instructions, and then he will speculatively execute the instructions. So the results of these instructions are not committed, but they are speculatively executed. So in this process, before accessing the variable A, he will go and access variable B, because he is doing a speculative execution. He is doing a prefetch, all of these instructions. So a lot of server hardwares can go and do a prefetch of instructions which are in hundreds. Like he can do a prefetch of 200 instructions, 300 instructions. It depends upon how many buffers hardware has, and what his pipeline is. But the server hardware does a lot of stuff like that to give the performance. So that's how the access of the variable B can happen before variable A. And in case there is no interdependency and those locations are not being accessed, then hardware will just use it, right? So that's how it will happen. So because of microarchitectural features of the hardware, location B can be accessed before location A. Okay, I think we answered all the questions. Thank you. Thank you once again for this opportunity, and all the best for future program.
Thank you. Thank you so much, Vinod sir, for the wonderful session.
Thanks.
So to all the participants, now we'll have a break of 15 minutes. So please do not get disconnected. Stay connected. We'll again start the session from 12:15. So we have a break of 15 minutes. And participants, please note that you have to join the Cisco WebEx platform through your registered email ID only. As this is the email ID, because only your registered email ID will be used to track your attendance. So if you join with any other email ID, so you will be marked absent, as the system generated file won't be able to detect your email ID. And please follow the Drive link that has been shared with you. All the important information, the course materials, everything will be uploaded in Drive on regular basis. So kindly keep following the Drive links. And yeah, and the YouTube, these sessions are also being streamed on YouTube. You can follow the YouTube link as reference for future purpose. If you want to use this, then you can continue watching the sessions on the YouTube. But please note that for your attendance, you have to attend the session through WebEx only. Yeah, that's all. Thank you. Thank you so much. And please do not get disconnected.
Hello.
Yes, hello, sir. Sir, can you hear me?
Yeah, I can hear you. Can you hear me?
Yes, sir, your audio is clear.
Okay, ठीक है,
So
ठीक
we
है. I
will
just
start the session after 10 minutes from
sure. I just wanted to
12:15.
test because I changed my device. I was viewing on something. I wanted this tab to be activated. That's what I thought. Yeah, sure. Okay.
Sir, you have been given the presenter rights, so you can test once.
Yeah.
When you are
I'll
able
do
to
that.
share your screen.
Yeah. 1 minute. I would be able to do that. Yes.
Yes, sir, your screen is visible. So we will
Okay.
start the session by 12:15.
No
Thank
issues. No issues. Yeah.
Hello. Good afternoon, sir. Can you hear me?
Yeah, I can hear you. Yes, I can. Yeah.
So it's 12:15. So we are going to start now.
Yeah. Whatever you say, have the participants come again and joined?
Yeah, sir. Participant count is increasing, so they are joining gradually.
Just wanted to know what is the background of these participants? Are they undergraduate students or of electronics, or it's a mix of electronics, computers, and everything?
Yeah, mostly the target audience are faculties from electronics background,
Okay.
and there are some students as well.
Okay. Sure.
Okay.
Yeah.
So, sir, before we start, we will have a short introduction.
Yeah. Please go ahead. Yeah.
So, dear participants, our next speaker is Dr. Satyadhan Chikeru, sir. So, Satyadhan Chikeru, sir, has received his BE degree in Electronics and Communication, MTech in CSE, and PhD in Computer and Information Sciences. He has served as faculty in various engineering colleges in India. Presently, he is with the Department of Computer Science and Engineering, KLE Technological University, Hubli, as a professor and head of Center for HPC. He has received various grants from industry and other organizations for research as well. He has published his research papers in various journals and conferences. Additionally, he is a referee for various international journals and conferences. His research interests include HPC, open hardware, AI and deep learning, parallel and multi-core programming, GPU programming, convergence of HPC and AI. He has received the Bolt Award from Air India for year 2008-2009. His biography has been profiled in Marcu's Who's Who in Science and Engineering for year 2007, Who's Who in World 2008, 12, 13, 14, and 16. So today we are fortunate enough to have Sir with us in this program as a speaker. So I request Sir to please start his lecture. The title of his lecture is Introduction, Microwatt Introduction. Over to you, Sir.
Yeah. Thank you, Firoza Madam, for the introduction, and good afternoon, everyone. So let me start with a very basic premise of what I'm going to speak today, right? Of course, agenda will follow. But the idea was that it has to be an interdisciplinary group of people who actually would be interested to develop a processor in itself, right, for a full functionality. And as AI is reaching its peak by various processors which are existing, people have started to develop their own processing devices, right, because of this open hardware culture which is coming up. And it actually requires an integration of faculties and ideas from both computer science as well as the electronics domain. So many of the speakers who would be speaking and continuing this workshop for the next 2 weeks would be from E&C department. I am from the computer science department with the intention that how this particular design, okay, concept could be actually brought down to the computer science stream, wherein not too much of VHDL, technicality, RTL, and all that stuff is involved, but computer scientists could actually use something like Python for developing their own processors, right? So this was the intention with which I started working with this group of researchers who are actually involved in this Open Power Foundation initiative, which is led by Ganeshan. So this is the whole overall picture of what I'm going to cover today as well in brief, and I'll show you some demo of how microwatt could be installed, run on a simulator on your system, which has a Linux environment, or it can be ported to a FPGA and run for certain preliminary very small type of printf, scanf type of stuff, right? Because it's a very initial core which we are trying to discuss. So this is what I would be covering. So let us start ahead, and feel free to ask me questions, and I would try my best to answer those. Even if I'm not able to answer, we will have some links which can be shared afterwards. Okay, so this is how it is. So the agenda is, how is that the components of a computer, right? Everybody knows the components of a computer, right? And everybody talks of this. So what I want is, if we talk of components of a computer, and how is it related, right, to basically a open source ecosystem, right? So this is the first agenda which we'll be covering. Then when we try to understand the levels of representation of how a program is executed, right, which we all know, but we'll try to recapitulate it once again and then try to understand how it is done. Then instruction set architecture, a perspective based on the complexity. You have already had 2 sessions actually on a broad idea of what an instruction set architecture means, right? And broadly, you know that various microprocessors, right, or various processing elements basically have their own instruction set architecture for that matter. So we'll try to understand the difference between those, which both the speakers before me also touched upon, right? And then what is actually a soft core processor? What are soft core processors? Okay, and how is it going to benefit the whole ecosystem for innovation? That's what we would be discussing. And then what is this microwatt? And then I will demo the microwatt on my system, as well as I will show you some snapshots and a video of porting that microwatt core onto a FPGA, right? So this is the overall agenda of the talk today. So let us go ahead and see what is that we are going to actually, 1 minute. Okay, so yeah, so let us try to understand this. This is basically the relationship between how an open source ecosystem going to benefit the component making of a computing element, or for that matter, a computer, right? So let us try to understand this. A processor, if you see that way, should have minimum all these things, right? It should have a program counter, it should have various registers, it will have an ALU in its own, and then there has to be memory, okay? And this memory will have the program memory as well as the data memory, and you will have your input output interfaces. And then there is a processor memory interface wherein you basically will like to have a communication between the memory which you are using and the processor which you want to execute some program, right? Now, this is where we were doing work since maybe 40-50 years, or maybe 2 decades or 3 decades. We were trying to work on a processor which was actually proprietary, right? Proprietary in the sense their instruction set architecture was well defined, right? And you needed permissions, and they fabricated the processors on their own, right? You take Intel processors, you take power processors from IBM, you take AMD processors. Each of these processors had basically all of this, right? And their instruction set architecture was a bit different, right? So what did it mean? It meant that they had their own design, which had control unit, which had the data path connectivities, which had its own address bus, which had the program counter, various types of registers, the ways in which the register behaved, changed, and then you had the arithmetic and logic unit, which were complex enough or which were simple, right? Based on this, the processor actually was being used. Now, when this type of a concept was there, everything was proprietary, and people did not have an option actually to develop their own processing element for that matter, right? So now comes this concept of open source ecosystem or open hardware, right? When this concept came, Now, when the open hardware concept came, so what effectively happened was people were able to actually, right, develop in their own processor cores. To add to that benefit, what actually happened was that got stuck. Anyway, so what actually happened was people could develop in their own processors. So slowly companies started open sourcing their ISA, right? That is what Open Power Foundation and IBM did together. They released their Power ISA 3, okay? And they open sourced it so that people could use that instruction set, develop in their own hardware, right? This is what actually happened. And same is the case with RISC-V or RISC-V, okay? So this was actually idea for people to develop in their own processing elements. So this is how all it started. And then let us try to understand the level of representation now. See, every one of us write high-level programs. 1 minute, I'll just stop this. I don't know, something gets stuck. Am I audible?
Yes, sir, you're audible.
Okay. I don't know, my pen is not working. Anyways, does not matter. Okay, so we have this high-level program which we generally use for actually solving a problem, right? Once we try to solve a problem in either of the high-level languages, maybe C, Python, Java, or whatever, right? Then it has to be compiled, and you basically end up in an intermediate assembly level language program. And that assembly level language program has to be converted to a machine language program. Now, this machine level language program is dependent on the hardware on which you are trying to run in your program, right? It is as good as that. So basically what effectively happens is you have your high level program. You, let us say you have A is equal to 2, B is equal to 3, and C is equal to A plus B. If this is the case, then this has to be converted to an equivalent machine level program, which basically is dependent on the hardware on which you are running. So effectively, it means that you will have to link it with the instruction set architecture of that particular processor. So I hope it's clear, right? So in that basic sense, your machine interpretation of your high level program, for example, if you are trying to use a RISC-V type of processor, or for that matter, open power ISA, or a microwatt, which is a soft core, okay, which has the ISA related to the open power thing, right? So your machine interpretation will depend on this hardware architecture description, which basically is this type of a stuff which is linked to your ISA. And then from the implementation point of view, this is implemented using this type of a logic circuit. So all the way from your high level to the logic circuit is something which the whole flow, if you are able to understand, then you can develop in your own processing elements, right? And that is where this workshop is going to be of help. What effectively you are trying to do is trying to develop something from this stage to a stage like this, wherein you can come up with your own processor element, I say, not a specific processor, maybe a processing element, which will be considered as a small processor to start with. It will be open source because your ISA is open source, and you can extend that ISA, right, to the instructions which you feel could be used with the processor or a processing element which you have designed, since you will add additional complexity to the existing processing core or the processing element which is, let us say, a microwatt type of stuff. Okay, so I hope this is clear, right? So this is where we are tending to do this workshop for the whole 2 weeks, and you should be in a position to develop your hardware at this level, but ultimately you should be able to link it up with something like a C program getting executed on top of it. So this is what is the initial thinking of how basically you should be developing your processor core. Okay, so this is how it's going to happen. So let us try to the next slide. Did I don't do the presentation? Is it 1 minute? Okay. Okay. So this is what I talked about. Now let us try to understand what a ISA is, right? I am telling it from the very, very basic things, because from tomorrow when you start working, right, these are certain things which you should be aware of, right? They may be appearing very simple or very, very primitive, but this is what is the overall thing which we should understand. Okay. So now let us try to understand what an instruction architecture proposes. So job of processing.
Hello. Hello, Satyadan sir.
Yeah, hello,
Hello,
madam.
Satyadan.
Somehow it got
Yeah.
disconnected. I'm again rejoining. Wait a minute.
Yeah. Okay, sir.
I don't know. Can you just give me the share access, please, again? I don't know.
So the sharing rights is with you only.
Okay. I'm not.
Okay. So you have joined another system. So let me, yeah. So shared.
Yeah, okay. 1 minute.
Yeah.
I don't know why this happened, but some disconnection happened. Yeah. So is it okay now? Yeah. Sorry for that.
Yes, sir. Yes,
Yeah.
sir.
So when you say the instructions are basically certain CPU primitive operations for the CPU, that basically means one thing which we should understand when CPU started was that instruction performed one after the other in sequence, right? So now, since we are talking of multi-cores, GPUs and all, this is not a necessity, right? This is generally not a condition. Instructions could be executed, okay, in parallel. But anyways, for the sake of simplicity, let us assume that a CPU is a single core machine and instructions are performed one after the other in a sequence, right? And we know that each instruction is going to do some small amount of work, and each instruction has an operation which is to be applied to the operands. and which might be used to change the sequence of instructions as well. So CPU, basically when you talk about, as we were discussing, there are particular set of instructions which need to be implemented based on the instruction set architecture. As I told you the examples, we have Intel 86, AMD, ARM, IBM PowerPC, RISC-V, Open Power Microwatt, and so many of the ISAs are now getting released, right? Because they have all become open source, open power, open hardware type of architectures with their own instruction set, right? Now, CPUs basically, that way if you see from implementation perspective, there can be two families. One is the CISC type of a processor and another one is RISC type of a processor. I'm not going into the details, but we should understand that we also know actually that RISC processor is more simpler, okay, and it has got less number of instructions as compared to CISC, whose architecture is a bit complex, which has got a lot of instructions, so on and so forth. But RISC is something which we would be starting with. So the instruction set architecture which we would be bothered about during this course is a RISC instruction set of open power, which basically is something like a microwatt. So it's a RISC-based ISA, right? So let us try to understand the early trends, right? Early trends where you add more instructions to new CPUs for making more elaborate operations. This basically made assembly level language programming easier. For example, VAX architecture, one of the very old architectures which was very considered powerful, had an instruction which directly could compute polynomials, right? So you could actually compute polynomials. Now, what effectively this meant, when the CPU design started, there was a stage wherein a lot of instructions were being pumped into for making the life of a programmer, okay, easier. So that meant you gave in a lot of instructions, so for which your ISA actually became complicated. Then in 1980s, we got this philosophy of RISC, wherein you actually kept the instruction set small and simple, and the idea was to build a faster hardware and let all the things, right, complicated operations and trying to understand how it's to be done was left to the compiler. So compiler used to generate the equivalent software for doing complicated operation by composing the simpler ones together, right? So this was the philosophy with RISC got developed, and till now, basically RISC is one of the very, very powerful architectures for people who want to design in their own systems, right? So that is how basically we are talking of this. Now, what is a soft core processor? In the morning, we heard about the ISA. So now we are, at least now we know that we are trying to work on a RISC processor. The RISC processor has got the ISA 3.0, which is compatible with open power. Okay. So this is how it's going to be linked. Now, what actually is a soft core? So a soft core processor, which we are talking of and which we will be seeing in the days to come, is microwatt, right? So microwatt is a soft core processor. And what does it mean? It means that it is implemented entirely in logic primitives of an FPGA using VHDL. This is a generic broad definition of a soft core processor. So we now know it's a RISC processor. It would basically be having the ISA 3.0 instruction set, which is freely available, which is royalty free, and that would be actually implemented, okay, on a FPGA using VHDL. That is what a soft core processor does. Now, one of the things which we should understand is that these core processors, okay, will not have any speed or performance characteristic. Okay, of a hardcore or a discrete processor. Please understand this, that this is a soft core processor which allows us to develop, okay, by adding or removing peripherals from the SoC with ease. So ultimately we are bothered about the SoC. So SoC will use a soft core processor, which is, let us say, microwatt, which has ISA 3.0 compliance. To this, I can add in my own instruction to elaborate this ISA or extend this ISA, for which, if needed, I would be adding in something to develop a SoC. This is the logic. Now, a soft core processor will also offer the flexibility of configuring the core for the application. So try understanding that our aim is to use this soft core for developing a processor specifically, right, for an application. Let us say now we have got a lot of AI applications, machine learning applications, all of these type of applications, right? Neuromorphic applications will require not a general purpose processor. Of course, GPUs are used for training, developing your own models and all that stuff. But when at inferencing, right, you don't require that type of a heavy hardware actually. You would be requiring a very, very small type of edge device, right? Now there, where inferencing comes into picture, there you can use these type of soft core processors to develop your own hardware for a specific application. It can be a computer vision application, it can be a healthcare application, or it can be any financial application, so on and so forth. So now using a SOPC solution or a SOC solution will offer flexibility outside the FPGA while designing the circuit board. So this also makes us feel good in a sense that once we are able to test it on a FPGA, and if it is serving our purpose, we can actually design it with our own circuit board with certain specific other things, which you will see as you attend the workshop. And now the idea is our SoC, if it exists in a FPGA, try understanding the concept that the pin out is flexible. So you are using a soft core processor, a minimal processor, okay, like microwatt, to develop your own processing element for a specific application, and you have ported it onto a FPGA. Now the idea is the pinout becomes very, very flexible when you try to develop it as a product. Okay, so it also gives us the complete freedom for component placement, right? As well as trying to meet the timing constraints. So these are certain specific advantages, okay, of trying to understand as to how soft core processors, ISA, RISC architecture, and the application onto a FPGA is going to actually complete the whole cycle, okay, of trying to develop in a processor. I hope this is clear. Any questions, please, till now? If there are any questions, you can please ask. Otherwise, I'll. Is there a question? Okay. Okay, so somebody asked me a question, SOC. It's a system on chip. That's what it means. SOC is a system on chip. Field programmable gate arrays. Okay, so I will show you a FPGA. Maybe let me just share it. Start the video and show you what it is. So if you see this, this is actually a FPGA board, okay, on which we have simulated the microwatt. So what effectively happens is, this is a bare metal board which has got this FPGA here, which is RT7, and this can be configured. It's a reconfigurable independent hardware, right? You can reconfigure this with whatever type of core I am trying to port it and test it. It has got various peripherals connected. Then when I put in my soft core, I need to link all of this so that it becomes actually a system on chip. Okay, so this is what it is. Okay, so I hope it is clear. So this is how it's going to be used in the days to come. Okay, so okay, so there are some questions which tells about, sir, you said that there is no speed performance guarantee, but when it is implemented as a product, we require both speed and performance. Okay, so the idea is this. See, when you are trying to test it, okay, when you are trying to test it and make it as your own processing element, okay, you are using a soft core, right? Soft cores are minimal cores which will help you to develop something on the open source ISA which people have given you. When you say that you want speed, you will have to develop associated communication mechanism, associated memory, associated IO devices, your bus, everything in such a manner that you can achieve the speed. It is not that it's not possible. Okay, it is surely possible, and that is what is important. For example, when you say the microwatt core, it supports in certain specific types of buses. So when you use a specific type of a bus, it has got its own speed, it has got its own constraints and pros and cons. So based on that, you choose which type of a bus. We will see that the majority of them support wishbone bus, right? So something like this. Gradually you will understand, but the idea is you will be able to do that, right? So what is the technology library file like 45 nanometer? Okay, so these are all fabrication things. You will see it in your last few 1 or 2 days, wherein how do you actually fabricate, okay, or try to come up with your own hardware, right? So I am not going into the details of it now, but the idea is as you go along this workshop, you will try to understand these technologies of fabrication from the experts, right, who work on this. So this is what, in brief, I can tell you that these are technologies which are used to manufacture those devices, right? So as far as I understand, right? So these are technologies which are used to manufacture, right? These are all manufacturing technologies. So this is what we are actually going to basically be doing in these 2 weeks of workshop, right? So let me start with the next slide. And yeah. Okay. So I hope you have understood the whole context, right, of using a soft core. Now let me just come to the open power microwatt. Okay. So as discussed, microwatt is an open source soft processor core originally written in VHDL by Anton Blackard at IBM. So as I told you that the soft core is actually implemented entirely in logic primitives of an FPGA using VHDL. So this is precisely what has been done for microwatt, right? And it adheres to Power ISA 3.0 instruction set and can be run on FPGA boards, booting Linux, MicroPython, and Zypher. Zypher is another OS, right? Real-time OS. So what does it mean? This means 1 minute. Let me again show you this video. Sorry, I will start my video. See, this basically means that this is a FPGA board. Onto this FPGA board, you are actually going to port in your microwatt. Okay, you are going to port in your microwatt soft core onto this. So this FPGA can now be treated as a microwatt processor which adheres to the Power ISA 3.0 instruction set. So whatever Power ISA instructions are there, that you can execute, okay, on this motherboard, treating this this FPGA as a microwatt processor effectively, right? But it will support. So it means that microwatt supports Power ISA. It's a soft core. It has been put here. But how is that the communication should happen? You will have to develop, right? And then you can boot Linux, you can boot MicroPython, and you can boot Zephyr. Is another operating system. So today I will show you in demo that MicroPython could be run on a microwatt, but we will be testing it on a simulator, okay, not on this hardware. But I will show you some other demo of this hardware as a video and show you the steps, right, which basically would be used for doing this type of an experiment. Okay, so this is how it is. So I hope I have made myself clear as to when you say that anything adheres to a Power ISA, what does it mean? And then you put a soft core onto the FPGA and you can use it to basically work as a generic processor by using by booting a Linux or a MicroPython or a Zephyr OS on it. Okay, so I got some question. I will check. Okay, any specification of a software processor? Yes, as the previous previous speaker also told, that we have got a lot of software processors available. RISC 5 is one of them, which started this momentum. Then Open Power ISA was released, and Open Power ISA is considered very powerful because it's a IBM standard proprietary ISA 3.0. So it has got a lot of facilities, right? So that is how it is, that much. You can search on the net, or I will show you certain software processor specifications, right? Anyone facing issues in seeing the video? I don't know, but video. Okay, sure. So that's how it is. I have not switched on my video. I only switch it when required because of the bandwidth constraint. That's it, nothing else. Yeah. So now let us try to understand it. I say microwatt is an open source soft processor core. It is a 64-bit core, bi-endian scalar integer processor core, which implements a subset of Power ISA 3.0 microset. Try understanding. It adheres to Power ISA 3.0 instruction set, but at present, this microwatt implements a subset of Power ISA instruction set. So this means not all the instructions would be implemented because you will have to write it, you will have to implement it, right? So this is a very, very minimal subset of Power ISA instructions, which you can expand as required, okay? Now, it has a 32 64-bit general purpose resistors and 32 64-bit floating point resistors. So this means you have got 64-bit resistors, which are general purpose in number, which are general purpose, as well as 64-bit floating point resistors, 32 in number. So you have 32 general purpose resistors of 64-bit width, and you have 32 64-bit width floating point resistors. And as I told you, it uses something called as a wishbone for memory interface. So you have a soft core, it runs on a FPGA, but to communicate with the memory, right, it gives you a support of the wishbone memory interface. Okay, so this is how it's going to happen. And at present, it has no memory management unit and no floating point unit. Please understand, since it does not have a memory management unit, to install or to boot any OS, right, you should have a memory management unit. So there are ways by which you can interface a MMU to this soft core and then boot Linux on it or Zephyr on it, on any operating system on it. Okay, so you will have to develop in the memory management unit, and then you have to basically do things, right? And then at present, you cannot work with any floating point operations because it does not have a floating point unit at present. So I hope this is clear. Okay, so let me just check on the questions. Okay, so there is a question asked which is talked about the little endian and big endian, right? So a bi-endian is something which basically means that it can support little endian as well as big endian order of processing. Okay, so this is how it is. Okay, so if you don't have floating point units, see the wishbone point at present, as I go along, maybe I'll tell you what it is. Okay, but it basically is for interfacing any memory, right? Let me just go back to the diagram if possible. But I showed you a diagram wherein there was a connectivity between the memory and the processor in the first stage, right? So what effectively happens is that communication has to happen through some system bus. And now this basic system bus has to be implemented. Now you can use Wishbone for doing it, right? That's what it is at present, right? So in detail, maybe we'll go sometimes, or we can go to some site and I'll tell you that. But for the time being, let us assume that there has to be some, what to say, mechanism, right, for trying to understand how basically communication happens. Okay, so I hope it is clear. So that's it is. Okay, so now what else? One more question. If it does not have floating point unit, then why do we have 32 floating point resistors? Okay, see here, having resistors is a different issue, and implementing that floating point unit is a different issue. Okay, so you will have to implement that, right? Resistors are just memory locations, right? Basically. So now the idea is that floating point unit has to be implemented by you, whereas a resistor is a static memory location which would be used for storing the data or trying to do things in that manner. I hope it's clear. Okay, so now somebody asked me about the wishbone. So okay, so let me just try to 1 minute, one by one I'm taking questions. So let me just try to understand and make you understand this, that wishbone, okay, is an open source again computer bus which is intended to let parts of an integrated circuit or the components in the circuit, as I told you, to communicate with each other, right? So many of these open source projects, right, basically use a bus, right? There are various other proprietary buses, right? For example, when you talk of NVIDIA, it has got NVLink, right? Which is between the GPU and the CPU. It's a proprietary bus. So each of these buses have their own interconnect protocols and ways by which these are to be used, right? So we're not going into the details at present, but this is how it's going to be discussed. Okay. Yeah. So let me just see the next question. Okay. One of the things is I have implemented hardware accelerators for FPU and tried interfacing with PIC32, done coding in VHDL. How can I compare my accelerator performance? What do you mean by this actually? Accelerator performance with regards to what? See, you cannot, if I am able to understand your question correctly, it basically means that you have implemented hardware accelerators for a floating point unit and you have interfaced with PIC32, right? So ultimately what you have tried to do is you have tried to interface your accelerator, right, as a co-processor with PIC32, and you have done the coding, everything on VHDL. You have to compare your performance, okay? Current method used to perform the FPU operations. Okay, so one of the things which I suggest, and it will be really very good, is that instead of PIC32, let us say, okay, you use RISC-V or maybe OpenPAR, okay, and then try to see how the accelerator is going to perform. That would be actually a very, very good work if you can do it with microwatt, I suppose. Yes. Because ultimately you are trying to develop your accelerator as a co-processor type of stuff, right? And if that can be added to your microwatt core, right, it becomes a totally different ecosystem wherein you are trying to develop in your own accelerator, floating point unit, or whatever. Yeah, if I have made your question right, if I have answered your question to that extent, you please do that. It will be useful. Okay, so okay, so let us go to the next slide and let us see. Okay, so as one of the speakers, earlier speakers also told that when you try to implement the microwatt, right, you have to understand these cycles. You have load and store operations, you can divide, you can multiply, you can do a write back. You have fetch 1, fetch 2, 2 fetch cycles, then 2 decode cycles and 1 execute cycle, right? So this has to be kept in mind for your instructions. So understand this, you have ISA, you have a set of instructions which you can use it with these cores, and then you basically have to understand the fetch cycle, the decode cycle, the execute cycle, and the write back, and then these operations. So this is how you are trying to implement that using your VHDL, right? A soft core has to be developed, instruction set is ISA, but you will have to understand this flow to develop it into a VHDL thing, which you can port it onto your FPGA, right? So let us try to understand this. Okay. Okay, so when I say core, okay, when I say core, okay, so when I say core, it means what? Let us try to understand this, right? Some of the things might not be very, very familiar, or you not be able to understand. But what I wanted to tell you is we will go to the site from where we have downloaded this microwatt. Okay, but the idea is when you are trying to develop a core, right, and you are trying to develop it in a VHDL, and you know that these are certain things which you will have to keep in mind. So let me just tell you what that core actually means. Okay, So that core, see, you should have your core actually is going to one minute. Okay. So, okay. So it basically again has this, right? Fetch 1.vhdl. So decode 1.vhdl, decode 2.vhdl. There is a register file, right? Then logical.vhdl. There has to be a count 0 type of stuff, right? Control unit, decoding, wishbone, okay? And then you have execute one, you have FPU, floating point unit, then load store one, MMU, decache, divider, PMU, write back. Okay, all of this has been implemented, okay, using VHDL. And then this particular thing, all of this, you will port it onto your FPGA, right? So this is how it's going to actually happen, okay? So I hope this all things are clear. Like you have cache RAM, you have core debugging facility. All of this is written in VHDL and is implemented. So let me just show you some demo snapshots, okay, of what is actually done and how it is done. Or maybe I will just take you to that site and share that with you first, and then maybe a minute. Okay, so are you able to see this website? Hello?
Yes, sir.
You are able to see the website now?
Yes, sir. The GitHub
Yes,
screen has
okay.
been opened.
Sure, sure. So if you see this microwatt GitHub page, okay, you will see that these are all the things which I showed you just now, right? And if you see this, they have simulated it using GHDL, which I will also show you. Okay, so the basic idea is that you have to actually first try to port your microwatt onto the FPGA or onto the simulator, and then you have your MicroPython actually installed on the microwatt. Without the hardware, if you want to test, you will have to use the GHDL simulator here. And if you want it to be built directly to the hardware target board, these are certain steps, okay, which are there, for which you will have to use, okay, Xilinx Vivado also. Otherwise, there are various other open source mechanisms by which you can do it. So this is one way of doing the synthesis. Okay, so we have done it using this, but in the workshop, you will try to come across various other methods as to purely open source, right? How you can do it. At present, we are using Vivado. So if you want to do it fully open source, right, there are mechanisms and methods which you will hear from the speakers. Okay, so once these steps are done, okay, you can actually be able to do what is being done here. Okay, so like you do all the steps, okay, it takes a lot of time, so I'll show you some snapshots of how do you build it. And then when you do this, okay, you do this, then basically you can work with your MicroPython, right? So this is what is on the GHDL simulator. We'll try to do this. And then when you want to port it onto the hardware, right, there are big, it will take a lot of time. So I cannot show you the demo, but I will show you the video and I will show you certain specific intermediate steps, which will help you to understand how an open source microwatt VHDL program could be ported on FPGA and what are the various phases you will have to undergo, right? So that snapshot of the things I will show you, right? So let us try to now stop this. 1 minute, some question. Okay, so no specific question as such. Okay, so done. So I will stop this. Okay, so now let me go to the thing which we have tried to do. Okay. So I hope this Linux thing is visible to you all. Okay. So if you see here, what we have tried to do is we have tried to actually make install everything, okay, using whatever was told on the website. So what effectively happens is you will end up trying to emulate the microwatt using a GHDL simulator. Okay, so if you go to the various folders, I will just try to take you to all of this and let us try to understand what each of these do. But for the time being, let us try to understand that I have now run MicroPython, okay, on the microwatt soft core. Of course, it is simulated and it is being simulated through GHDL, and I am able to view it. But ultimately, I am able to run MicroPython on the PowerPC. Okay, so this is what is the microwatt stuff. And if you see, it is able to do some preliminary operations, right? Using Python instructions, right? The idea here is it is going to be very, very slow because it has to actually go through your keyboard input to the this thing, right? See, it's very, very slow. So once you type, you won't be able to get it so fast. So I am now trying to do some delete operation and show you, because through your system's keyboard, right, through your OS, then to the microwatt, and then it has to give you the result back on the simulator through GHDL. So it's a very slow process to test it. But once you put it on the hardware, there are various other issues which we will talk about. But the idea is that you would be able to do things. Now, if you see this, why I had put the operation result and kept it for you is that it will take few seconds, okay, or minutes for this result to appear actually, because it is running on a very, very preliminary soft core microwatt, which is actually being simulated on my Ubuntu. Okay, so this is how it's going to happen. So it will take some time. Let us wait for a few sec. And in the meantime, if you have any questions, you can ask me. Otherwise, it's fine. We will wait up till the result comes. Okay, so there are some questions. Wait a minute, I'll try to answer them. Yeah, so yeah. Can we work this on Windows? In the sense, I am working on Windows in a sense that you can use WSL, but you will have to use open source because you are talking of open hardware, open software. Obviously, it has to run on an open OS, right? So yeah, so what I have tried to do is, if you are asking me a question on whether you can work on Windows purely, then I don't think so. But Windows has WSL or Ubuntu, which you can install. That's what I have also done, right? And then you can work on it. So this is actually Windows basically running WSL. And then, yeah, so that's why that is one other thing that it has become slow, but yes, so the result is going to come. Yeah. So yeah, how MicroPython is ported, you have to follow the steps which are given on the GitHub page, and you can do that. Yes. But try understanding that when you directly port it onto the hardware, okay, the problem will be that since your UART communication, okay, is not very supportive of it, and then your OS also has to run. So up till you actually boot a OS on which your Python is running, okay, it becomes a difficult thing for directly running a Python instance on the FPGA board. Yeah, so this is what actually we are also trying to do. Yes. Yeah. So it will take time. So yeah. So what we can do is, if you see this, it will take a few minutes. So what I suggest you people is, tonight you basically can do that installation by yourself. One of the things which you can keep in mind is that you will have to install the GHDL and this tool chain, GCC tool chain. Okay, when you are trying to install it either on Ubuntu or Debian or whatever. Okay, so of course on Mac it has got some issues. Don't worry about it. Don't go in with Mac, but try to either use WSL on Windows with Ubuntu or Debian. Anything is going to work fine. And then most probably you can work directly on a Ubuntu standalone system as well, and then try to actually do the same procedure, right? Whichever is given on the GitHub page, so that your this thing, okay, your at least you will understand that your microwatt is running on the emulator mode on that thing using GHDL simulator. You can at least work with MicroPython. Okay, so this much, if you do it tonight, that it will be good. Try it out. I could have actually I could have sent you that you can install this, that, everything, but that would consume a lot of time. So that's why I wanted to show you, so that you have a feel that, okay, it can be done. And then you go step by step. So this is how it's going to happen. So this is your microwatt core. You have micro Python here. Okay. And then you have got various things. If you go to the FPGA thing here, you have the FPGA, and then the Hello World program and Wishbone and all of this, right? So let me just see why it's taking so much time. It should come now. Anyway, so it will come in the meantime. So let me show you how we tried doing it. So I'm waiting for that to complete its execution so that Yeah. So you see that now you are able to see that it has given you 2. Okay. So are you able to see? Hello.
Yes, sir.
You are able to see this 2 which has come as a result of the sum of 1 and 1. Okay.
Yes, sir. Yes, sir.
So thank you. So what I am going to do is I'm going to now stop this and let me just show you the steps once again if people are interested on microwatt as to how it is to be done. I'm going to the same website and I will share this. Yeah. So if you see this, the first step, if you want to do this, is to see there are 2 things to doing it. One is that you will have to have the PowerPC 64LE Power 8 tool chain. This is the first thing, okay, which you want to do, because you are trying to actually build something for PowerPC 64 and you are trying to use something which is not PowerPC. So you need to have a cross compiler. Okay. So the first thing is you will have to install this tool chain, PowerPC 64 LE Power 8 tool chain, and you have to set up the cross compiler environment. Okay. Once you do this, you can download MicroPython and then use these steps, make it, and then understand this, that you will have to use a simulator, right? You can directly download a pre-built MicroPython image, or you can build your own, then use it. One of the things is Microwatt uses this GHDL for simulation. So you will have to either install it or build it using LLVM or GCC as a backend, right? So the best thing is to use GCC backend, but GHDL with LLVM backend is easier to build, but LLVM is something which is there in your Macs. So if you have got good feel of working with LLVM backend, then also it's good. Otherwise, you can work with GCC, not an issue. And then if people are very well conversant with using Dockers, you can use Dockers also. Okay, and Podman also. And then you can actually generate, okay, your firmware, okay, to be actually put into your RAM, and then you run that and then try to actually see the output. And if you really want to synthesize it, you will have to actually use the Vivado, use FuseSock, and then use all of these packages based on whether you are using Fedora or whether you are using Ubuntu, and then try to actually replace this target, okay, this with the board which you are using, and then try to put in your RAM initial file, okay, which either will be a hello world or any program, okay. And then how do you connect? See, now the point is you want to run something on that target, you will have put that, but you will have to have a communication between your board, okay, and the display. Because you don't have a OS on it, right? You will have to use certain serial port communication. We have used Picocom. So you can use anything, and then basically you can run in your all small programs, and you can either build microwatt, but when you want to see that microwatt stuff, right, you should have a OS onto thing, right? So MicroPython should run on OS. So this is how it is. So this is what you are supposed to be doing. Please try it out, and I'll show you some things of when you want to port it, okay, onto the actual hardware. Okay, so see here, this is at a stage wherein we are trying to use a Xilinx CS server, okay, for actually trying to generate, okay, a bit stream for our FPGA. So we have to do this. So this is in the end. Once you are able to do this, that your FPGA stream for whatever FPGA you are trying to port is successfully generated, that is where you end it. But while you want to do it, okay, I will show you in detail all the steps. But once you are able to get this, you port it onto your FPGA, which I showed you just now. And then if you see here, the output tells that terminal is ready. And we have written a small program to read in some data from the keyboard. Okay, it's our own function which we have written, and we have used Picocom here. So this is the UART setting for serial communication through the keyboard, and then this is how we get it. Okay, 1 minute. Okay, so these are two snapshots, and I'll show you the video actually, and then I'll discuss the details of how it is done. I'll stop this now. Okay, so I will show you a video first. It's a very small video actually. Okay, I'll share this and maybe let me run this. So this is the time wherein we are trying to communicate onto this microwatt, which is actually put onto this Nexus A7 board. Okay, and when we are trying to write in something through that particular keyboard, see, this is when we have put in our FPGA bit stream onto the FPGA. So this is where it is successfully showing us, and then the communication, when it's happening, it is being shown by this green LED here, okay, which is a blinking LED. Okay, so this is how we tried to do it, and we are successful. And I'll show you now the various steps for porting it. So let me just show you this. I'll share another thing of mine, which will start with certain. Yes, so okay. So let me just show you this. Let me just show you this in a sense that what are the various steps which you require, okay, which you will have to show, okay. So there are various phases, right? So let me just come to the phase wherein you are trying to do some global iteration of trying to do this. This is related to your VHDL and optimization layout and all that stuff. So at that point I have reached wherein you basically have this global iterations for number of nodes with overlaps, okay, and then what is the intermediate timing summary, then how is that global iteration 2 happens, then you have this phase delay and skew optimization being done, okay, and some of these things are there wherein when you talk of phase 4 technically, right, you have this rip up and reroute of number of nodes with your overlaps, then global iteration 0, global iteration 1 I showed you, and then if you see phase 3, you have got the initial routing to be done, okay, wherein you have this launch clock and capture clock, right? Then you have this pre-routing and updating of the timing, then initial routing happens here, okay. So what are the top 5 pins with tight setup and all this? This is very, very niche of people who work on VHDL and stuffs like that. So I basically work from the computing science aspect. So some of the things, right, even I am not very confident if you ask me some questions, but the idea is to give you an idea of how basically, this whole phase, right, from Vivado is basically linked. So if you see the starting of the routing task, you have the phase 1 build for the RT design, then router initialization, then pre-route cleanup, and then updating of the timing. All of these steps are linked, right? Then you have this placer report wherein you have this placements, right, north, east, southwest direction. How is that the global congestion and short congestion happens, and then print estimate, and then the final placement done, because this FPGA is reconfigurable. Once you do this all, then you put it onto your FPGA and it implements the same thing. So phase 1 of physical synthesis, right? All of this is linked and it does actually. So here you have your LUT combination physical synthesis in the placer, right? How many cells were added, how many cells were removed and optimized. And then something of that type wherein floor planning is also done. Okay, so netlist actually is generated, and then you have, okay, these placer and all I told you already. So something like this, then power optimization is done, then all of this actually is done in various phases. So you have all of these phases, how much cells were created, okay, then connectivity testing, then optimization phase again, then cache timing, then ultimately you basically have your thing running, designing, everything done, and then you come up with a stage wherein everything is completed and you get that particular thing which I showed you previously of everything is successful, and then try to do this. So I suppose this is what I wanted to talk about. Yeah, so so if you see this, this is what all we covered. 1 minute. Yeah. So let me just Here again, my this thing, and yeah, so these are certain references which I thought I'll show you in the end, that there were some slides from the course at Berkeley, and then of course this GitHub page of Anton Blakard with Microwatt. So I suppose this is what I thought I'll do. And if possible, if you are interested, you basically can start working on trying to install things and trying to do things. Maybe otherwise I don't have any other things. So yeah, so that is done. Yeah. Yeah. Firoza ma'am, I'm done.
Okay, sir. So let's see if the participants have any queries or not.
Yes, yes. Let me
Yeah.
just see
So
that.
participants, if you have any queries regarding to this session or lecture, please put it in the Q&A session.
Yeah, they have
Please
put, let
put-
me just see this.
Yeah.
I implemented 1 minute. Okay, it would have been better with live demo of generating bit file and configuration of the FPGA. Yes, so I suppose this is what you are going to do from tomorrow, right? This was just a precursor to what you would all be doing in the days to come. I'm not telling that this we will not cover. This is what you are going to cover in the hands-on tomorrow morning, I suppose. Yes. So because live demo is going to take a lot of time. Of course, I could have done the video of it and done it. So instead of generating a video, I just took the snapshots and I'm showing it to you. Otherwise, anyways, you would be doing this in the days to come. Yeah. So because before configuring FPGA, practically lot many issues comes on the way. If seen, we will get confidence. Yeah, I understand that. So tomorrow, anyways, you are going to do it. It's all hands-on which you are going to do in the next 2 weeks, right? So you will see all of this. I just don't want, I didn't want to do everything in one go because other speakers and other experts would be handling that for you. I just wanted to give you an overall picture of how microwatt is being used. Yeah, that's it. Or how you can use it. So that was the intention of just 1 hour of thing, because in 1 hour I could not explain everything, right? So that was the only reason. Yes. Okay, so 1 minute, some other question. Yeah, there are few questions. So 1 minute. Let me go to the scrolling up this. Yes, after configuring FPGA, I think we also have to port required software to interact with the hardware. Okay, so the idea is this precisely. See, your FPGA will have just a microwatt core. So you will have, when you say you have to port required software to interact with the hardware, that is what you are going to develop. Precisely, that's what you are going to work with. Okay, you will have to develop the software such that it interacts with the additional hardware which is there. Correct? That hardware ultimately is going to be decided by you because you are developing your own processor. Okay. If you have that Nexus board handy that you showed, can you please show which on the board pins you shorted while uploading the bit stream? I mean those blue caps which are used to change modes. Okay, yes, this is one very, very important question. Yes, that's a good question actually. So one of the things is, 1 minute, I will tell you this. Okay, I will actually share with you that thing again. 1 minute, I will have to switch on my video. Okay, So the question which is asked is this, and I feel that it's a good question. I would like to show you that. I don't know how, but anyways, let me just show you this. See, there is, I'll remove this. There is this particular blue pin here. This is this particular blue pin here, okay, which is adjacent to your power thing, right? Or the USB power port. This has to be between the USB and this. Generally, this is set like this to the opposite end. So what's going to happen is, even if you connect your USB, you would not be able to get anything. So you will have to connect this to the USB and the middle one. Okay. And then I suppose you have this SD card and USB stuff. So SD card, you can keep it. And then this thing has to be put on the JTAG. Okay, so this has to be put on the JTAG. Yes. This anyway you will come to know once you use your board. But yes, you will have to keep it between your USB, because you are using a USB communication port connected to a system. So that one, this has to be at the SD, or you can keep it at USB based on whatever you are using. And this has to be the JTAG stuff. Okay. Yeah, if I have made myself clear. Okay, commands are required to do MicroPython program. Yes, yes, yes. And what's a Docker image file or any special software? Okay. So the idea is this, that I don't know how many of you have worked on something like virtualization. So you have this thing like trying to run your Linux operating system on Windows using virtual softwares, which has hypervisor and stuffs like that. So here, instead of that, you use something which is called as a Docker. So Docker actually does not have this particular thing of hypervisor more technically, so that it basically is an emulation of that particular operating system on the existing operating system. So you can have a Docker image for running Ubuntu on Windows. It is something like a virtual box which you use, or virtualization softwares which you use. Docker is one of the types of virtualizing environment, but which does not have a hypervisor. Yes. Or any other special software? I could not get this question, but yeah, I suppose I answered almost all the questions.
Yes, sir. So almost all the questions are answered. And so participants, if you have any more queries, you can put. So like some participants are asking in the Telegram group, like what to do, like what to download if they are having the OS as Windows. If they are having Windows operating system.
So okay, let me share my screen and do it step by step. At least we will do that. Okay. So let me just share my screen. 1 minute. Let me share my screen, share it. And then see, if this is your Windows 10 or whatever you're talking of, then what you have to do is you have to go to Microsoft. What is it? It's coming. No, not Dolby Access. Where is it?
Satyadhan, sir, your voice is breaking.
It's not clear?
No, sir, it's still breaking.
Okay, 1 minute. I don't know why this Dolby thing came automatically. It's 1 minute, something. I don't know. Am I audible?
Yes, sir. Yes, sir.
Okay, so if I connect to the Microsoft, what is it, market or whatever they call it as, 1 minute, let me see this. Yeah, Microsoft Store, right? So one of the things what you can do is you can go to Microsoft Store, okay, it will show you something like this, and there actually there is something like WSL. Okay, so that basically is, or you can type Ubuntu for that matter, right? So you have got this, see, Ubuntu 20.04 or Ubuntu 18.04, right? You actually can install this, okay, on your Windows. So what effectively happens is, once you install this, you can actually 1 minute, I'll show you. Once you install this, okay, if you directly type Ubuntu, you would have installed it, and once you open it, right, you will get your Linux prompt. But that is for sure that directly you cannot work on Windows. You will have to work on Ubuntu or any other Linux version. Okay, so once you get it, see, you get all the facilities for Linux. See, this is what I have also done. So I have used Windows intentionally. Actually, I work on Debian. I have a standalone system in the lab, but intentionally I chose Windows. On the Windows, I chose Ubuntu this thing, Ubuntu's image using WSL. I installed it. It's very simple, as I told you. Once you are able to do it, you can work on Linux using Windows. I hope I have made things clear. Stop the screen. So some more questions. So let me just see what is it. Yes. So I suppose there are no other questions. Or do you have any other questions in the Telegram group or something which you are talking of? Then yes. Hello.
Yes, sir.
Yeah. So I suppose there are no other questions which have come up. So yeah. So it's already 150. I
Yeah.
suppose.
Yes, sir. Yes, sir. So, but as we are having no more queries in the Q&A window, so we may end today's session here, right, sir?
Yes, please. Thank you, Firoza
Okay.
madam, for
Yeah.
giving.
Thank you, Satyadhan, sir. Yeah. Thank you, Satyadhan sir, for today's session, informative session, and I hope so all the queries of participants have also been addressed.
Yeah.
And
If
sir, tomorrow
anybody-
also we are having your session.
Hello?
Yeah, hello, sir.
Yes? Hello?
Yeah, hello, sir.
Yeah, madam. Yes.
Ma'am.
So that's it, madam. Thank
Yeah,
you so very
sir.
much. Yeah.
Yeah, so tomorrow also we are having your session. So
Tomorrow, okay.
Yeah.
I think there's a mix-up, I suppose. Somebody else was supposed to take. Anyways, that's fine, Firoza. We'll have a call on it. Yeah, sure.
yeah, I think it's Varun sir or it's so.
Yes. Yeah,
Thank you.
sure.
Thank you, sir, and thank you all the participants for attending the session. So please keep visiting the drive link for all the updates.
Yeah. Thank you so much.
And please join for tomorrow's session. The same link will be used. And please join with your registered email ID only using the same link. Thank you. Thank you all.
Thank you all.
Thank
Bye.
you again. What's